Hello and welcome to today's webinar. You will learn about the new generator circuit breaker, the HB1-C. And this is our all-in-one solution for retrofit and more. And what this more means, you will learn in a few seconds. I'm Michaela Münnekes. Some of you might already know me from our electrification and automation webinars, or if you visited one of the exhibitions in the last year, I might have been your tour guide there. And so today I will give you a guided tour through this webinar. And I will start with the round of experts that I gladly welcome today here in the studio. So my first colleague here for you is my dear colleague, Fabian Rademacher. Welcome, Fabian. And Fabian is an experienced application engineer for generator breaker switchgear, and he's deeply involved in the development of the HB1C. My next guest here is my dear colleague, Hong. And Hong Urbanek is an experienced engineer for generator applications and for vacuum technology in medium voltage. And to complete the round, I gladly welcome Edouard Desplanches. Edouard is an experienced portfolio manager for generator circuit breaker systems and an expert for the HB1C. And why do we have three experts here? Let's take a glimpse into the agenda and see what they will present to you. And we will start with Fabian, telling us about standards, and he will give also a comparison of version or of standardization versions 2015 to 2021 or 2015 this way. So we'll start with Fabian first, learning on standards there. Then we will continue the webinar with Hong, telling us about the generator circuit breaker for synchronous condenser applications. And last but not least, we will have Edouard here on stage introducing the new generator circuit breaker, the HB1C. And we want to make you part of this webinar. And that means please type in your questions to the experts during their presentations. And at the end of each presentation, we will take some time for your questions. I will be your voice. I will read your question to the experts, and they should be able to answer the question. So after each of the session, we will have a short question block. We will have a short break. I think all of us might then need a short bio break, and then we'll meet again for the next part of the agenda. And so maybe you still remember, we will start with Fabian telling us on standards. So Hong and Edouard, I'll see you in, I think, about an hour. Thank you so far. See you later. And Fabian, let's know about or give us a deep dive into standards around circuit breakers there. Thank you.
Thank you very much, Monica. Michaela Münnekes. So important to use a generator circuit breaker compared to the distribution circuit breaker. And then afterwards, as I hope a lot of you will know, we have changed, or the committee of the IEC board has changed the standard 2 years ago into a newer version. So I want to quickly give you an overview what has changed and why is it so very important.
Let's wait a second because I have some comments around audio. Is that fine? Audio is fine? We're not sure. Just give us a few seconds and we'll...
You're not linked.
Better?
I think it should work.
Okay. Let's see.
You have to use that one.
Yeah. So we have a backup microphone and that should work in a second. Get everything again fine? Thanks for the comments. So I think
I
now
will
it's your
start
turn
again, and I can.
Yeah.
I hope I do get your name correctly. So thank you very much, Michaela, for introducing me. So my name is Fabian Rademacher. I'm working for the GBS, for the generator breaker switchgears within Siemens since 2018, and I will give you a very short introduction today about the generator circuit breaker application compared to the distribution circuit breaker, which I hope all of you will know. Give you the overview why you need a generator circuit breaker in your generation network. And then afterwards, of course, since we have a small change in the standard, a new version, I will also give you a brief introduction which changed in the past. And hopefully afterwards, you are very familiar with that and enjoy. All right. Then, as I said, what we are talking about today in the first presentation, in the first part of this webinar, we will talk about a typical generation layout, why we do need a generator circuit breaker. Afterwards, I will tell you quickly about the advantages of a generator circuit breaker. We are going to compare the generator circuit breaker, which you might know from Siemens, with the distribution circuit breaker. Afterwards, we are going to discuss the latest changes in the standard. And then, of course, I want to give you some key takeaways that you are prepared in the future, what you have to really consider for a generator circuit breaker and a generator breaker switchgear. Okay, a typical layout for a power plant is that you have a generator and a turbine set, of course, as a power generation unit. This one is connected via an IPB, SIB, so a different busbar system to the generator step-up transformer, most commonly used or abbreviated by GSUT, which I also will use in the slides. So be prepared that you are getting this abbreviation for that. And in between, this has changed. We are going to have most probably and most likely we need this generator circuit breaker to protect your assets. So in case of short circuit currents, this generator circuit breaker will protect your assets in terms of a short circuit. So this is really important to know. And as a first glimpse and to give you an idea, distribution circuit breakers are not able to clear these faults which will occur in the generation network. So I will actually give you an idea why is it so important? What are the advantages of a GCB compared to a distribution circuit breaker first? Okay, first of all, as I've already said, with the generator circuit breaker, we can improve the protection. So we are not only protecting from its name, generator circuit breaker, the generator, but we can also protect the transformer and auxiliary transformer, depending on the position and the location of the generator circuit breaker. We can also improve the increased power plant availability by having higher selectivity of the power plant, just by switching off each single unit, or to be able to switch off each single unit for maintenance reasons. So we don't have to shut down the whole power plant, but only a specific branch. We can, of course, if we do have to shut down the grid with the generator turbine set, we can also still supply our auxiliary services via the generator. So we are kind of independent with the generator circuit breaker. And of course, and last but not least, but a very important characteristic for a generator circuit breaker is that we can provide a synchronization between the generator on the one side and the generator step-up transformer on the other side. So as you know, we have a rotating voltage for the generator and the rotating voltage for the generator step-up transformer with the grid. And being not synchronized would lead to an out-of-phase fault, which will be part of the next part by my colleague Kong. She will explain she will quickly explain what is an out-of-phase fault also, and I actually don't want to spoiler that. And of course, all in all, the generator circuit breaker can increase the security of your power plant and also can increase the availability of it. So next step is, it's very important to understand that with the generator circuit breaker, or not only with the generator circuit breaker, we do have different unit protection concepts. We do have 3 different classes. Class A is for all electrical faults of the generator, generator transformer, unit auxiliary transformer. It is very important that we are switching off the generator and turbine immediately and simultaneously. Then we do have Class B. This is for all turbine faults. In that case, we are just shutting down the turbine and afterwards the generator. And Class C is for all faults beyond the generator system. In that case, we are only tripping the circuit breaker at the high voltage side, and this will allow us to let the turbine run and the generator continues to feed the auxiliary transformer. Okay, let's consider the tripping Class A, or the unit protection Class A. The Class A, if we do have a serious electrical fault without a GCB, this would mean that we have to trip all of our equipment downwards of the high voltage circuit breaker, so we will shut down the whole power plant. Of course, the selectivity is not given at all. When considering and when installing a GCB between the generator step-up transformer or your medium voltage transformer and your generator, you can have 2 different classes A. Class 1A, A1 is mainly for the faults in the generator step-up transformer and the auxiliary transformer. In that case, you will increase the protection and the faster shutdown of the generator step-up transformer. And for Class A2, this is mainly for faults in the generator. There you can decrease with the generator circuit breaker the time to restart with uninterrupted power to the unit bus and the auxiliaries. So you can clearly see that your GCB is bringing you a huge benefit in selectivity and availability of your power plant. Furthermore, generator circuit breaker are not only protecting your generator, but they also can protect your generator step-up transformer. So let's imagine we can have different kind of failures in a generator step-up transformer. This can be different kind of shortings at the HV conductor, of the MV conductor. We can have different kind of flashovers and so on with different type of probabilities. And of course, the highest probability does not mean that it will be the highest or the most severe damage for your step-up transformer. Of course not. But with these different kind of failures, the generator step-up transformer can have a very high raise of the pressure inside its tank. So, and this will lead to a generator step-up transformer rupture, we call it that way, as a potential damage. Without a generator circuit breaker, this might happen. When installing a generator circuit breaker in between, or let's say first without a generator circuit breaker, what is actually happening? We have a fault which is inside the generator step-up transformer, totally independent whether it is shortage or whatever it can be. We do have a feeding from the system to the generator step-up transformer to the fault location, and we also do have an amount of feeding from the generator to the step-up transformer. Due to the high voltage circuit breaker, we can switch off the amount of short circuit current from the high voltage system, of course. But since the generator is still feeding the fault to the generator step-up transformer, the resulting overpressure over time will increase even more. And this will lead to the fact that we are having or exceeding the limit of our tank capability. So at the crossing point of the tank capability and the overpressure inside the tank, we're going to have a generator step-up transformer explosion. So it will explode and you have to replace that. So considering a generator circuit breaker in between the generator step-up transformer and generator, this will lead to the same experience, of course, for the high voltage system. So our high voltage circuit breaker will trip and will cut off the short circuit current which is fed by the system. And the generator circuit breaker will also simultaneously trip and will cut off and switch off the short circuit current which is fed by the generator. And in that case, our generator step-up transformer and the tank is safe for being exploding. That's why first, this is very important to keep that in mind, why we do need a generator circuit breaker, or why we do need a circuit breaker in between the generator and the generator step-up transformer. Of course, you might know generator circuit breakers are a very specific topic. They are so important, so specific, that there are only a few companies who can supply that. We do have, and you might have asked the question, or you might ask the question, why can't we take a normal distribution circuit breaker in between? Since with the generator circuit breaker and the distribution circuit breaker, we have to fulfill the same needs. We do need the sufficient insulation, of course, between the phases, between phase to ground. We need to carry the continuous current with minimal losses. And we do need, of course, one of the most important, reliable interruption of rated current and short circuit currents. But as you might know, and as I have already said, generator circuit breaker and distribution circuit breaker are not the same. That's why we are not type testing a generator circuit breaker to the standard which applies for the distribution circuit breaker. And that's actually the reason why I want actually also to highlight the differences in between, that you understand the need of having an own standard for being type testing, or for having a type tested generator circuit breaker. On the one side, when we are considering a generation network, we have a very short connection between the generator and the generator step-up transformer. This will lead to a very low earth capacitance, of course. Due to the generator, we do have a very high system inductance. And most important, what is not covered by the generator circuit breaker standard or by the generator circuit breaker system standard is that we are just having a switching duty which is nearly purely inductive. Comparing the generation network to the distribution network with the switching duties, which are mainly inductive and capacitive, based on the lower system inductance, long transmission lines and the cables, leading to a higher earth capacitance, you get the idea why we need the specific type of standard. And this will also lead to a different kind of short circuit characteristics. So for a generator circuit breaker, we do have two different short circuit ratings. The first rating is the generator source rating. So in that case, we are type testing, and we are testing our generator circuit breaker with a fault which is fed from the generator over the generator circuit breaker. Thank you very much. In that case, what we see, due to the high degree degree of asymmetry, we do have delayed current zeros for a generator source short circuit current when switching off a generator source short circuit current. On the other side, when we, of course, as I said, we do not only have a generator source breaking capability, but we also do have a system source breaking capability. In that case, we have to consider a fault location between the generator and the generator circuit breaker. So that means that our generator circuit breaker does not clear the fault which is fed by the generator, but it will clear the fault which is fed by the system. So the high voltage grid being in line with the generator step-up transformer. And what we can see is that we do not have any delayed current zero because of the decaying of DC amount, but even more important is a constant AC amount. And this will lead to a very fast zero crossing after contact parting time, and the generator circuit breaker is able to immediately cut off the short circuit current for a system source. And if you consider the distribution network, this is actually quite comparable to the switching duty for the generator circuit breaker for a system source rating. What we also see is that we do have a constant AC amount of short circuit current, slowly but surely decaying of DC amount of the short circuit current, but we do not have any delayed current zeros due to this having immediately a zero crossing. That's very important. And this is actually the perfect case for a distribution circuit breaker, but distribution circuit breakers are not type tested for this delayed current zero, the generator source rating. And that's why we do need this generator circuit breaker in between. Of course, any current interruption will lead to a transient recovery voltage and a rate of rise recovery voltage. In that case, it is quite important that, of course, for generation networks, due to the small amount of capacitance and the high amount of inductances, we do have a very high steepness of the transient recovery voltage, the rate of rise recovery voltage. And it also has a higher frequency. Comparing it to the distribution network, what you can see is that we do have a smaller frequency, and also the peak of the transient recovery voltage is much smaller. So also for this specific characteristic of the short circuit current and the transient recovery voltage, our our generator circuit breakers are type tested for this specific requirement. Of course, and if we are just comparing it one by one, what you can see is that generator circuit breaker are being type tested for more severe conditions as distribution circuit breakers. And of course, what I've said is that we do have different standards. And now we are really coming to the standard. I don't want to highlight the IEC 62271-100, this is the distribution circuit breaker standard, but I do want to highlight the IEC IEEE 62271-37013, which is the generator circuit breaker system standard, which was updated 1.5 years ago. So if you're just comparing both of them, the generator circuit breaker standard was originally founded or written, first released in the year 2015. It was updated in October. It was October 2021, and covering the same structure as the original, or not the original, but the base standard 62271-1. One important wording, one important point, which directly came into your mind when reading the standard, is that they have implemented a new wording. We are not talking about generator circuit breaker as a standalone unit anymore, but we are talking about generator circuit breaker systems. Generator circuit breaker system is covering all the additional equipment you can find in your generator breaker switchgear, such as back-to-back switches, disconnecting switches, earthing switches, and last but not least, it also covers the enclosure if it's applicable. So this is one of the major points which have been changed in the latest version. Then we do have, or they have implemented the mechanical class M3. I will go into deeper that in some seconds. They have also implemented the functionality of T-off switches. T-off switches are switches which are located in auxiliary branches, and they will give you a guidance how to select and how to design these T-off switches. They have introduced the topic of low frequency switching, which will become important for new applications in the generator circuit breaker systems applications or usability. Of course, since we are not talking about generator circuit breaker itself anymore, but about the system, you will also get updated information about the rating plate. But thankfully, the general test parameters compared to the version of 2015 did not change. So type tests being performed through the former version of the standards are still valid. So let me just focus on some important points. And to compare the standard 2015 with the standard 2021, the versions. With the version 2015, of course, this was actually the first release of both of the standard, and the IEC matched with the IEEE standard. In that case, it is always better to have one standard than nothing. It is only covering a single GCB. It also describes the influence of an IPB connection in terms of temperature rise at the IPBs, temperature rises inside your generator circuit breaker, but that's it actually. For the version 2022, when going to the wording generator circuit breaker system, they are also covering disconnectors, they're covering the earthing switches. They all need to be type tested, no, not type tested, but they will give you information how the whole system will work together specifically. The enclosure, which was not part of the version 2015, is now one integral part of the GCP system, as long as it is applicable. Of course, the influence of the IPB connection is still valid and is still given in the standard. And last but not least, for the GCP system, we are getting always asked how to define a current path. In that case, the standard committee will give you a very clear and hard definition on how to design and how to select the current path. So there's actually no need to, for example, for a main branch having just one ingoing, one outgoing without any auxiliary branch, to select it and to design it on the sum of both short circuit current, but only on the higher stress, depending on whether it is the system source rating or the generator source rating. And of course, we do have the perfect example for a generator circuit breaker system, which is going to be introduced by my colleague Edouard Desplanches, I guess in 1.5 hours. What we can see here is a generator circuit breaker, which you all know from Siemens. We do have an inline integrated main disconnectors, and we do have earthing switches at the generator and at the transformer side. This device, what you can see here, is really type tested as per the latest version of this IEC IEEE standard. So it covers already all the points I have mentioned for a GCP system so far. Furthermore, of course, since the energy market and the power generation market is changing, you might know that the standard committee has released or introduced a new mechanical class, which is M3. M3 means that you have higher operating cycle or a higher amount of operating cycles, up to 10,000 times, or at least 10,000 times. The mechanical classes M1 and M2, which were released and introduced in the very first version of the standard, remain the same, but they have added the mechanical class M3 for up to 10,000 operating cycles, as I already said. So it will also give you an idea, and you can compare different equipment based on the mechanical classes. But it's important to say that it is possible also for us as suppliers to have different mechanical classes on each and every generator circuit breaker system. So it is not needed to have a mechanical class M3 for all the equipment we have for our generator circuit breaker system, but we can mix it up in between, just as an information. And of course, we do have the T-off switches. T-off switches is a switch which is located and which is installed not in the main generator branch, but in an auxiliary branch. There we also have to simulate and to consider two different kinds of failures. One failure is between for example, between the unit auxiliary transformer and the generator circuit breaker. And the other failure is between the generator circuit breaker and the connection to the main generation branch. It has clearly to be said that we have to simulate these kind of faults very thoroughly. Since what you can imagine is when we are considering fault location F2 and our T-off generator circuit breaker just have to cut off or to clear the short circuit current, which is fed from the unit auxiliary transformer. This is only a very small amount of it. So we are talking most probably in the range of 1 to 2 kiloamps for small unit auxiliary transformers, up to maybe 5 to 10 kiloamps for some bigger unit auxiliary transformers. But since it has a direct connection to the generation branch and we are considering fault location F1, we do have to consider the sum of the step-up transformer, and we also do have to consider the generator. So even this generator circuit breaker being located in the auxiliary branch will have a very small rated current rating. It most probably it will have the highest short circuit breaking capability in your network. And the version 2021 gives you the idea, and I really want to highlight that they are saying a T-off breaker has to be, when being installed in a generation network, has to be a generator circuit breaker. And that's why we also simulating that to be sure that we can also protect your unit auxiliary transformer, for example. And then I already want to come to the key takeaways. Most important, what I've already introduced are the T-off switches. T-off switches are described, defined in the standard now. They need to be generator circuit breakers. We do have the new wording generator circuit breaker system. So we are not only covering the generator circuit breaker as a current interrupting device anymore, but we are talking about and we are defining a whole bunch of equipment being installed in an enclosure in your generation network. Type tested GCBs, which were formerly type tested as per the version 2015, the type tests will stay valid. So there is no need to update these type tests. Furthermore, the standard, the newer version of the standard, will also give you an explanation on how to design a switchgear and the current path of the switchgear. So also not to over exceed or to over dimension your switchgear, but to have a very perfect fit for the occurring short circuit currents in your system. And of course, we have new definitions added, some small changes in wording, such as mechanical classes. There were also some small changes, as I said, in wording, which we do not have such a high impact on the understanding of a system. But we are in line with the original standard, which all 62271 standards are rely on. So this is the -1. So you can compare it one by one, and that's actually it. So do not, if you have any questions, you can directly ask it to me. We will try our best to answer it. Otherwise, we will come back to you later.
Yeah, Fabian, I already have some questions seen here in the row. So thank you so far. I once again learned something. That's why I love to moderate these webinars. Still on my learning curve. And let's see, I think I take the first two questions on my own because AP wanted some innovation of new product range, and I think we'll come to that. You will
Correct.
learn throughout this webinar about the innovations there. And KA wants to visit and see things live and needs an invitation. And I think there your local sales representative would be a perfect partner to communicate, because from out of headquarters, we are not there in the regions. But now let's go into the technical questions, because FD wants to know, are there any EMTP circuit breaker benchmark models to use in a digital simulation?
Thanks for the question. There's actually a huge branch and a huge bunch of software which you can use. We as Siemens, we are commonly using PSS Netomac, which is a licensed product. We do have some very good experience with that, but of course, there isn't a need that you are just using PSS Netomac. You can also use some other kinds of EMTP models, EMTP simulation software, of course.
Perfect, thank you. So yes, there is quite a few on the market. And the next question directly concerning already the HB1C, and we'll see if that's a question for you or if we take it later on to Edouard, but we'll start right here. ZF wants to know, does your new generator circuit breaker, the HB1C, have energy reducing features, so ERMS, for arc flash mitigation?
I actually want to keep this question for Edouard.
Okay,
so he will be the expert for the HB1C. very deep into the development.
Yes,
I'm quite
I
familiar
thought
with
so.
the HV1C, but it is his
Yeah.
job.
And CT, I think your question came in rather early before the presentation, why to use the new generator circuit breaker HB1C. And I think in the course of this webinar, we will see some of the application cases, not only because
Sure.
how to configure the network and why there is a difference between a generator circuit breaker and a distribution network circuit breaker, but also where does exactly this HB1C will fit in. So stay tuned. Edouard will tell you why you should use the HB1C. Next question is placed in, I think, Spanish. My Spanish is more than poor. I know nothing. We will take that question to the experts later. We will do the translation and then you will get an answer. And that brings me to our question and answer feature. The questions you brought in will be answered by the experts here in the studio as far as they can, and they will be answered in a written format later on. And then you will get access to the recording, to the presentation, and to the questions and answers. But stay tuned, we take most of them right here audible. The next one that came in from GR is also something I will not read right here because it's a range of things that are statements. We'll try to see if that will bring a question later on. How does the generator circuit breaker work? That's something that PA wants to know. You will see that later on when Edouard will describe exactly the HB1C. There are schematics, how it works, and you will see more of it. And then next question is once again one for me. KN wants to know, is there any certification of attendance awarded after the webinar? Well, this is not a training where we monitor your attendance rate. This is just a webinar for your information. So in case your company allows you to write down learning hours, that's something you can do if you think you learned something, but we are not in the position to hand out certificates for this webinar. Nevertheless, we hope that you learned something already and that you will learn something throughout the webinar. So then the question, what's the voltage of the input and the output? So the rated voltage level for the circuit breaker.
I would say
right?
it's the circuit breaker, and since we are talking today about the HV1C, I would actually highlight that it can handle up to 24 kV of input voltage and of course output voltage. It's a rated voltage.
Yeah, perfect. Thank you. And then we had in the chat the question, and Gerhard, thanks for copying it. RR wanted to know, where are these classes, these A, B, C out of? And I think you came to that later, right? That's yours.
That is mine. Correct. This is not directly out of a standard. This is directly taken out of a paper. Once you will get this presentation, you will also find the source of it, and you can read about this different classes A, B, C. So you will get the source. It is clear written there. Perfect.
And then another question for me. I think we had some of those already in the chat, because FO wants to know how to join the team. So Team Siemens, yeah, you're kindly welcome to apply for any kind of job at ours. Siemens.com/jobs is the target there. We here are not in the position to monitor that. We have our people and organization office there, but feel free to apply. We are always in search of new and handy people. Next one, that's a technical one. What are the tested X and R, and I think I know that in German, but not in English, values for this generator circuit breaker? You will know.
Correct. It's actually the impedance ratio, and we are fully type tested as per the standard. I would also give it later to Hong, not to spoil any question, because we do have a direct link in between, and just to keep you interested in this webinar series or in this webinar today,
ABR,
we keep you.
stay tuned. So, but can we tell something about the minimum opening time?
Yes, it's depending on the breaker.
Okay.
For the HV1C and the 3H37, we are talking about opening times of 40 milliseconds in that range.
Okay, thanks. So, and let's see, read the flyer. I got this. Oh, let's see. Okay, let me take AIM's question to you. Coming from Indonesia, thanks for that information. I was reading the flyer and I got this product information, free maintenance, which sounds good. And yes, it is. Is there anything that I must pay attention to when we run inspection, or is there any point we should pay attention to in schedule time to make sure it's still proper and in good condition? Yeah, what's the basis of maintenance free? Yeah.
The basis of maintenance free, I also want to direct this question to Ida, but what I can already spoil about that.
Yes, please.
Is we do have the different mechanical classes, what I've introduced to you. And since we are talking mechanical class M3 for the generator circuit breaker HV1C system, we can be sure that we do have a really high amount of switching operations after having the need for maintenance. So this is quite good. And afterwards, of course,
more information.
We can discuss later.
Yeah, please place your question again. If Edouard's presentation will not answer that sufficiently.
Correct.
And then thanks Gerhard for copying all of this. This is also once again my invitation. We have this little chat area where all we speakers can say hi and something like this. And what I do monitor during the presentation is the field that's called questions. And so different areas, but you already see wherever you type something in, I have my producer in the background and he copies your question to make sure that we reach our experts. So we had the tested values and now AA wants to know. For scheme comparison, two generators both connect to the step-up transformer of 4.5 megawatt ampere. What are the recommended protection criteria for this setup? Do I need to consider overfluxing protection, considering that the generator is combined gas and heat type?
Well, what I actually can say is that the generator circuit breaker standard is only covering a rated power above 15 MVA. So actually the 4.5 MVA is quite below the requirement of installing a generator circuit breaker. But of course, we can simulate the application, and based on the results of the simulation, we can recommend the specific type of protection.
Perfect. So it's not the HB1C, but a different...
It will be another type of circuit breaker.
Yeah. So, and then there was the question how it differs in protection from the conventional circuit breaker.
I guess we are talking about the difference between F6 and vacuum. Or are we talking about the distribution circuit breakers and generator circuit breakers? So generator circuit breakers are able to withstand these delayed current zeros. So the thermal stress for generator circuit breakers is much higher, and they are type tested to handle this thermal stress. Distribution circuit breakers, there isn't the need to type test it, and that's why we can also do not give any answer about the behavior for a prolonged arcing time. So
okay, so different tasks, different protection schemes. Yep, fully understand. And now that's something mechanical in the transformer tank. Let's see if that's specific for this webinar, but nevertheless, thanks for the question, because CP wants to know. The pressure inside the tank of the transformer is much slower, thermal and mechanical, than the excitation regulator, the electrical. How can it be, how can we explain the possible damage of the transformer's tank?
Thank you. Yeah.
Let's see if we can explain that.
We can explain, but I want to take this question to my home and to
Yeah.
think about that. We will come back to you. You will definitely get the answer in a written
Perfect.
form. And then
Yeah, thanks. Yep, as I already mentioned, not all questions can be answered right here, and we want to deliver correct answers and comprehensive answers. That's why we, in addition, deliver this the written format of the answers. So let's see the next one from AA, and let's see. The stringent requirement dictates that the distance between the generator and the generator circuit breaker should be as minimum as reasonable possible. So let's say about 15 meters, considering that SC Analytics, and now that's an abbreviation I don't know, analysis has been done on the scheme to the grid connection. Do you think providing higher transient fault rating with a generator circuit breaker is reasonable?
I actually, personally, I don't like the way to have a higher or longer connections between generator and generator step-up transformer. So, as already written, we should keep as small as possible, also to also decrease the losses in between.
Yeah, and save cablings and whatever. I mean, just put them close to each other. But if you have the requirement there, so for whatever reason, come back to us later on and get into a 101 discussion on that. Mm. So let's see, we have still more questions in the line. The shorter the time, so from CP coming in, the shorter the time of the fault disconnecting, the larger the DC part of the fault's current. And can you give some hints about the principle of the arc fault extinguish inside the generator circuit breaker?
Then we are talking about vacuum again, and about the principle of extinguishing arcs in vacuum, depending on our contact system, whether it is an AMF, so an axial magnetic field, or a radial magnetic field contact system. We do have either a rotating magnetic field in between, or we do have an arc. Well, we do have multiple arcs burning in between. And the circuit breaker, the generator circuit breaker, is just, yes, we'll just interrupt the fault until the next zero crossing. Further insights, as you might know, it's kind of a secret.
Okay, yeah. So we know what you're talking about there. I understand at least half of it, and you see there's some technology hidden inside. But thanks for the question. So let's see. I think more questions to come. AA wants to know, is it possible to refurbish a panel comprising both generator circuit breaker and non-generator circuit breaker connecting the generators to step-up transformers?
I guess this is the perfect question for my colleague Eduard afterwards. He will give you some very brief introduction how this can be done.
That's
and we
true.
Give you hands-on.
Yeah, that's exactly something that Eduard has got in his presentation, because I've already had a sneak peek into that. You will learn on that and get information on that in, I think, a bit more than an hour. And let's see, the T-off breakers allows to integrate solutions such as IS limiters. So to put it in a question, do the T-off breakers allow to integrate solutions such as IS limiters? For generator SFCs, this is important.
If you want to do that.
Okay, so it's possible.
It's possible.
It's possible. The short answer is yes, it is possible to integrate. So, and the next one is also concerning the T-off generator circuit breaker. ABR wants to know, are you saying that T-off generator circuit breaker should have a higher rating as a generator circuit breaker?
It depends. So that's why we are simulating the whole application. And based on the simulation results, we can recommend the perfect fit for the T-off circuit breaker.
Okay, thanks. And I think we will take time for one last question. That is coming from AK. What is the minimum generator rating for which generator circuit breakers are recommended? If the generator of a rating 15 megawatts is directly connected to the 11 kV board, then the generator circuit breaker is required, or is a normal distribution breaker recommended?
I do understand the question. That's why the standard is always giving us the need to simulate the whole application. And it cannot be clearly said if we do have a real cut at the 15 MVA. The standard is saying, all right, or is covering an application having a higher rated power than 15 MVA. Then it is directly recommending a generator circuit breaker. But of course, there might be a small gap where a distribution circuit breaker might be suitable. Might be. We have to simulate that.
That's why we simulate, right. And can we take one more question?
Yeah,
I think we can. So interesting right now. So CP wants to know, in order to avoid a T-off circuit breaker as performant as the generator circuit breaker, maybe we can open first the generator circuit breaker and make sure that the T-off circuit breaker is able to bear the dynamic and thermal strength during the fault for some tens of milliseconds.
Yeah.
Interesting scheme. Okay.
If you do find a distribution circuit breaker, we are talking about generator circuit breakers with a switching capability of at least 50 or 40 kA going up to 110 kA, and being in the range of having a higher generator circuit breaker rating of 63 kA, there isn't any distribution circuit breaker which can provide a higher breaking cap or a higher a higher class or an even stronger circuit breaker. So you definitely need to go to the generator circuit breaker to be able to handle the thermal and the mechanical stress.
Okay, thanks. So there you go. Can distribution type circuit breakers be proven to be acceptable for generator applications despite part 013?
If you do the type testing and if it passes the type testing, you can also have a distribution circuit breaker. But if you want to spend some money,
yeah, you can do the type testing there, or just take the type tested version that we provide. Okay. So I think, thank you so far. We will now go into a short break, give your eyes and your ears a little rest, and we'll meet again on my clock. It's then 2 o'clock. So at the full hour right now, in about 7 minutes from now on. And we'll meet again, and then we'll see Hong, and she will explain to you, or she will introduce the generator circuit breaker for synchronous condenser application. So see you in a few minutes, and thanks for your questions so far. Stay as vivid as you are out there.
Steht hier M3T2.
Hey, and welcome back. I hope that you enjoyed a short break and that you are now fit again for the second part of this webinar, because we will have Hong here in the studio telling you how the generator circuit breaker is a perfect application for the synchronous condenser, or something vice versa. She's the expert there. And yeah, please remember to make use of your possibility to ask your questions to the expert. You already made intensive use of the questions tool. Please continue that. Hong will answer as many as possible after her presentation. So let's know about synchronous condenser applications. Thank you.
Thank you. All right, I've seen already a few questions of you guys, so I try to incorporate it maybe in my presentation. And if not, at the end, of course, we will explain that or answer the questions which has been shown. All right, you have already heard the first part, which is presented by Fabian about the standards comparisons. And now I'm going to give you a brief overview about the specific application within this very niche field of products. So I'm going to present an overview about the use or the application of vacuum generator circuit breaker in, or let's say, for synchronous condenser applications. So we will start with the part where I give you, let's say, about some info, some insights about why to use a synchronous condenser, what is the idea behind using these applications. And secondly, we would go into details about which kind of let's say requirements GCB has to face when dealing with synchronous condenser. And last but not least, I'm going to give you some info what we have done in few feasibility studies with our vacuum generator circuit breaker, especially for synchronous condenser applications. So let's start with a brief overview about the, let's say, the application field where you would use vacuum generator circuit breakers. So I think it is already a well-known fact that vacuum switching media is widely used in the medium voltage for the last 40, 50 years. And especially vacuum generator circuit breakers are used actually at the moment mainly in the conventional power generation. You can find that in conventional power plants, hydro pump storage, depending on what is the rating and depending on what the requirements about the switching numbers, which is required from the power plants itself. We have at the moment in the field around about almost 4,000 GCB units, which has been installed. So actually a quite great installed base with our Siemens vacuum generator circuit breaker, mainly in power generation. A small part of that are being used in oil and gas applications. And then a little bit, let's say, larger portion of that are being used into utilities and industries. So beside the arc furnace and data center applications, of course, you can find the synchronous condenser applications, which, let's say, is being protected with the vacuum generator circuit breaker. So what is the reason behind using synchronous condenser? The challenges, what we are having right now in the power grid is the trend is going into reducing the use of nuclear and fossil power of power plants, which is ongoing. And because of that reason, there is a lack of short circuit power, of course, in the grid, which can cause stability problems in the high voltage grid. And in addition to that, of course, when you reduce the use of nuclear power or a different kind of power, you need to find kind of alternatives, and that's why the renewables power plants or power generations come into the question, such as PV and of course wind power, which can cause, of course, stress to the power grid. The next, let's say, factor which contribute to this grid problem or grid challenges is that the international transit trade of electricity is growing. So that might cause, let's say, further stress and burden for the transmission network. So all of these challenges are resulting into problems that, as I mentioned before, we might have a problem with the lack of short circuit power in the grid. And those kind of problems will lead to voltage and frequency instability in form of swings in the grid. And of course, by reducing the use of certain power plant types, you will not have, let's say, a great number of generators which can produce reactive power, which leads to some difficulty when coming into power factor regulations. So all of these challenges and problems, let's say, ask for the use of, ask for a solution how to solve these kind of problems. So there are different solutions right now in the market dealing with these kind of problems. For example, of course, you can use synchronous condenser. You can use, let's say, transformer combination to solve these kind of power factor regulations. And also there are different kind of capacitor banks to solve these kind of power factor issue. However, it has been established that using synchronous condenser has been widely used. Of course, the reason behind that is mainly because the solution is quite flexible in regulating the power factor. And the second point is, of course, using synchronous machines to regulate power. You can also provide the network with the short circuit power, which is actually missing here and which we have identified as challenge. All right, so we just have a glimpse about why is this important or what is the application field of using synchronous condenser. But as you guys remember that this webinar is about GCB. So I would like to jump into the next slide, talking about when using synchronous condenser, what are the challenges a GCB is facing. So to show you that, I would like to use an example of a conventional power plant, because at the end, the main challenges for the GCB is similar, whether you use that in conventional power plants or you can use this for synchronous condenser. So as you can see here is an example of how a combined cycle power plant looks like. To highlight right here is we have a generator circuit breaker, or GCB, is connecting the generator step-up transformer and the generator. Depending on the size of the power plant, that means the connection can be realized via isolated phase bus bar. It can be by normal bus bar or cable. And one point we can see right now is that the connection between generator and GCB is quite short. So because of that reason, you have, when it's translating into an electric network, we have a very highly inductive circuit in generator circuit or generator applications. So that means we might have a very short circuit current with high degree of asymmetry. Secondly is, of course, normal generator usually start with the power of 10 or even more megawatt. And we know for a fact that for synchronous condenser, the machine itself, even at the same power, they have very small short circuit reactances, which leads to very high short circuit current level. So that's for a fact, that's the challenge what the GCB has to face. And of course, depending on the power, GCB has to face a very high continuous operating current. You have listened to Fabian's session before that depending on the machine type and machine parameters, a circuit breaker or GCB might have to face delayed current zeros. The reason for that, we will come to that in the next slides. And of course, as you can see, we have a very short connection between generator and GCB. That means the capacitance in the circuit is very small. And we just mentioned, or you just remember, we have a high inductance in the circuit because of inductivity, like generator and transformer in the grid. And we have a very small capacitance, so which leads to a very high and steep transient recovery voltage when interrupting those kind of current. So all of these, let's say 5 challenges are challenging for a GCB to solve. And now I would like to go a little bit into the technical detail, how that come to the question. So these 2 terms you have seen before, we are dealing with generator circuit breaker. So that is why there is a standard which has presented by Fabian. So this standard introduce 2 terms. So we have to deal with system source short circuit current, and the other terms is generator source short circuit current. So let's start with the right-hand side with the system source short circuit current. So basically, if a short circuit happens at the generator side of the GCB, then the current across the GCB will be fed by the system. The system means high voltage grid and transformer. So basically, every short circuit current is consisting of 2 components. We have the red part right here is the oscillating AC current. And you can see that it's normal. I think it's like the AC signal is very well known. And we have a constant amplitude of the current, which is fine. On the other hand side, you can see that there is an offset of the current, which is the direct current component. This current component is decaying. And this decaying of this direct current component is, let's say, determined by the grid X to R ratio. So I will come back right now to the question which has been asked in the chat. The IEC IEEE standard mentioned that every generator circuit breaker has to be tested with the time constant of 133 milliseconds. So there's an equation where you can translate the time constant using the frequency of your network into the X to R ratio. And if I remember correctly, it would be an X to R ratio of 50 per unit. But we can calculate that later. All right. So that is about system source short circuit. As you can see, we have a constant AC and decaying DC components, but let's say at every time we always have a current 0. And just to remember, in the medium voltage, you need a current 0 for the circuit breaker to clear the current, any kind of current, not only the short circuit. So the challenge for a circuit breaker for interrupting system source short circuit current is only that the DC component, that means this offset, is higher than in case of the distribution circuit breaker. Okay, we cover that part. And then let's go to the left-hand side. We have the generator source short circuit. As you can see, the breaker is the same. The set of generator and transformer is the same, but now the short circuit will happen at the transformer side of the GCB. So that's why the current across the circuit breaker right now is fed by the generator. And as you can see, we have 2 components, the AC component, which is oscillating, and the decaying component as a direct current component at the right-hand side. Generator itself is a highly inductive component, so that's why its DC component or armature time constant, which is written in the data sheet, is quite large. So that's why you have a very slow decaying behavior, what you can see here in this graph. And then secondly, generator itself, a synchronous generator, doesn't have only the main winding as a transformer. And depending on the design and depending on the manufacturer, you can have the, of course, the field winding, because we need an excitation for a synchronous machine. And then third, there might be a damping or damper winding, depending on how the design looks like. You might need that for stability, mechanical stability of the machine itself. So because of these 3 sets of different windings, in case of a short circuit, they will interact with each other. in the process. And that's the results of that is that you can see here that the AC component decays as well. So if you would combine these two components, AC and DC, you might see a typical curve right here, that the short circuit current of the generator source fault can have delayed current zero. Delayed current zero means you don't have current zero to a certain extent. Okay, I cannot show that right now. And you remember, I just mentioned that in the medium voltage, any circuit breaker needs a current zero to interrupt those kind of current. So that asks for special requirements for GCB that besides having to deal with high DC components, around about 70 or let's say 60% DC, a generator circuit breaker has always to deal with delayed current zero issues. That means you have to test a circuit breaker for a certain long arcing time. So that is a specific requirements from the standard in which every generator circuit breaker has to fulfill. And then a third, let's say, task of the GCB. You have seen, of course, any circuit breaker of any sort has to be able to interrupt a short circuit current. We cover that with system source and generator source. But another task of the GCB is, of course, to synchronize the generator with the grid, because otherwise it doesn't make sense to have a generator. So basically, in the modern system right now, metering system, the possibility to have any kind of failure is quite low, because the system itself will detect what is the voltage level, what is the phase shifting between the generator and the grid. However, during maintenance, or let's say during installation, there might be wiring errors. So it can be that some service technician will, let's say, mistaking the two phases when connecting the wiring. So because of this reason, it might be possible that you will have false synchronization. And false synchronization means when you close a circuit breaker, a GCB, it will not, the generator and the network will not be in phase. So if that happens, you might have a typical curve of out of phase current, which looks like that. And the rapid movement of the rotor inside the generator will cause this current constriction, what you can see here. So in such a case, when you open the circuit breaker, you can see that there is a very high offset, even though the current itself is very small. And that is, of course, a special requirement what a generator circuit breaker has to be tested for as well. And to that point we come to later, because we did cover that in our third part of this session with the simulation and feasibility study regarding this out of phase fault. All right, so we have talked about the characteristic of how short circuit current and out of phase current looks like when a short circuit happens in the synchronous machine, and of course, especially in synchronous condenser. There are, let's say, there is a standard existing explaining how to test the GCB, and of course, the same standard does define as well what are the conditions to prove the suitability of a GCB in general. And this is this IEC IEEE standard, which Fabian had explained in the previous session. So they clearly say what are the points, what you have to take into account when doing simulation. So that's the overview of that I'm going to give you right now. So we start with the fact that actually all generator applications, motor application in the medium voltage, they are operated with the isolated start point or with the highly impedance start point. And because of that reason, the maximum short circuit current level you can get is if a three-phase short circuit happens. And that is what we have to do when simulating short circuits, let's say when we're doing simulation, for simulation. Secondly is about what is the fault resistance when initiating the short circuit. We know for a fact that generator itself can operate in different operating points. And the standards clearly mention that if the generator is at no load, and a short circuit happens, you have to simulate that case without any external fault resistance, but you have to consider the arc voltage of the circuit breaker. When it comes to the fact that the generator is already in service, like in, I don't know, overexciting, underexcited, lagging and leading operating points, then you have to consider, of course, the arc voltage of the circuit breaker itself. And additionally, you have to consider also the the arc fault with a minimum arc fault of 300 volts. In real case, it depends on where the short circuit location will happen, whether this is in, let's say, in oil or in air, and what are the distances of the bushing. You can define a different level of arc fault for your case. However, we try to stick to the standard to simulate the worst case, so we use the 300 volt as recommended. Then additionally, you know that we have in the application itself, there is a phase shifting between voltage and current. So that does have an effect on the short circuit current itself at the end. So therefore, we always simulate the short circuit current in two different times, I would say. First of all, we simulate that at the voltage 0, that you can see in the upper part of this diagram. So we have the same set of machines and network, only that the short circuit initiation is a different time. And you can see that when the short circuit happens at the voltage 0, you would have a maximum peak current, which is here. So you have a maximum offset when that happens. And by simulating that, you can see what is the maximum offset of the system, what is the maximum peak. And the maximum peak current, of course, means the maximum mechanical stress for the contact system and for the whole system. And then the second case, what we simulate, or we always simulate because it's required by the standards, is that if the short circuit happens at the voltage maximum, that's in the lower part of this diagram, you can see. If that happens, we can see that one phase, which is indicated here as phase R, we have 0 offset. And if that happens, and this phase is cleared first, you can see that the other 2 remaining phases will have the maximum DC offset. And by doing so, we intentionally simulate this case. You can see that the arcing time in that case is higher than in the upper case. So by simulating these 2 cases separately from each other, we can get the first results, maximum mechanical stress for the breaker because of the peak current. And here we can get the maximum arcing time, which is the maximum thermal stress on the contact system. Right. So I just mentioned briefly in the last slide that the arc voltage of the GCB has to be taken into account when simulating interruption or short circuit current. So basically, at the instance of the at the instance of the opening of the circuit breaker, any sorts, you always have an arc initiation. So by doing that, you can see that in the equation, which is written here, that the decaying of the short circuit current itself is influenced by the reactance of the system and, of course, of the resistance. And by having an arc voltage, you have increased the resistance or the resistive component of the circuit. And as you can see here in my lower diagram right now, the dotted line is how it normally looks like without any opening and interruption. And the solid line is what it looks like when you have an effect of an arc inside in this equation. I do want to emphasize the fact that there is a misleading information about that vacuum circuit breaker in general doesn't have any effect, or let's say doesn't have, or the arc inside the vacuum generator circuit breaker doesn't have an effect, which is actually proven wrong. Vacuum switching technology does have quite small value in comparison to SSX or oil generator circuit breaker, but it does have an effect on reducing the arcing time, which we can see here. So it is a real case and real simulation we have done, and as the project, I'd say, delivered. And as you can see that in the lower part of the simulation of the same set, you do not consider any arc voltage here. And of course, that is the normal simulation, what, let's say, any consultant can do. But we are the manufacturer of the GCB, of the vacuum GCB. So we have the internal knowledge about the characteristic of the vacuum arc. And we have to implement that as requested by the standard to provide our customer with the new simulation, including the effect of an arc of the GCB. And as you can actually see that I do not count how many periods it will be in the lower diagram, but we do, but the arc in the vacuum does have an effect to reducing the arcing time. And that's what we have to do, and that's what we provide to our customer to prove that using vacuum, or let's say the vacuum generator circuit breaker is suitable for generator application in general. And of course, the same is what we are doing with GCB, with generator applications. We do that with the synchronous condenser application as well. All right, so that was a general input about simulations. I would like to go into the operation of generators in general, and of course, an except of that would be how synchronous condenser is operating. So with the machines manufactured, there are existing different kind of capability curve depending on the design, depending on the build and type of the machine itself. So you know that the stator with its major current set a certain limitation of the capability curve. And of course, with field winding or the field current excitation, you can set another limit for working of the generator itself. So based on all this information, you would have a capability curve, of course, given by your machine manufacturer, which define the working zone or the operating area of a synchronous machine, either condenser or generator. So by doing that, based on that, we can use this information and see how much we can incorporate that in our simulation. What we can see in general is that if the field current, excitation current is larger than 100%, then we are talking about the machine delivering reactive power into the grid or into the network or whatever is connected to. And in such a case, we might have a higher short circuit current at the end. And on the other hand side, if you have an under excitation mode, like if the excitation current is less than 100%, then you are consuming the reactive power from the grid. And therefore, in such a case, the short circuit current, the amplitude, will be smaller. And how does it look like? And what is the reason behind that? You can see that in this phasor diagram I'm trying to draw. Every machine, every rotating machine can either work in motor mode or in generator mode. And for the synchronous machine, you have, of course, the terminal voltage, which is like where the GCB, for example, is connected to. But the driving, let's say the driving voltage for the short circuit current is the internal induced voltage. And the amplitude or the value of this internal voltage, it depending on which operating mode the generator is working. And by using this phasor diagram, you can see that in under-excited mode, the internal voltage UP right here is smaller than the terminal voltage. And on the other hand side, if you're working in the overexcited mode, then the internal induced voltage will be larger. And that is the reason, because this voltage is the driving voltage for the short circuit current. And this is why you have higher current amplitude in overexcitation and lower short circuit current values when working under excitation. Another point with what we have found out is here's a direct comparison in the capability curve of a synchronous generator in the upper hand side, and it's the blue diagram. And in the lower diagram, you can see the capability curve of the synchronous condenser, both of them are in the similar range of power. You can see that the synchronous condenser does cover higher range of reactive power, and I mean that's what the machine is used for, because we want to provide, of course, on one hand the short circuit power to the grid, but on the other hand we want to regulate the power factor in the grid. So that's why our aim is, or the aim of using synchronous condenser is sometimes just to provide reactive power, and I want to go as much as possible into 0.1 power factor. So that's like the main working capability, operating area of a synchronous condenser. And in the direct comparison, of course, you can see that generator itself covers only the smaller range of the capability curve, because they tend to use in the rated operating point to provide reactive and active power. But for regulation, of course, you go into the edge of the machine, and so that's why synchronous condenser covers more or less the limits of the machine. As already mentioned before, when doing direct comparison of the short circuit current or short circuit behavior, we have found out that the operating point does have an influence on the short circuit current value and the short circuit current behavior. We always see that the lagging power factor or overexcitation shows higher short circuit current. So that means the breaking current is of course higher, and of course this, the peak current itself is of course also higher. However, on the other hand, the leading power factor delivers the highest asymmetry, because you've seen before the current value itself reduces, while the DC component in the system still remains the same. So in direct comparison, you would see a higher offset in case of leading power factor or in underexcitation, which is all explained in this, let's say, simplification of phasor diagram. Well, we just spoke about the general input and how much the operating points influences the short circuit current behavior. One of the main jobs, as I mentioned before, is the synchronization of the generator and the grid. So what happens to the system if we have a false synchronization? And there's a term induced in the standard, which is called the out of phase switching duty. That means we intentionally test the case where the synchronization is not in phase. As it has been found out that the amplitude of the out of phase voltage, of course, depending on the out of phase angle. You can have generator and system in phase. That means the out of phase angle would be 0. Or you can have the out of phase angle of 90 degrees, which is written in the standard, and you have to test it for. Or you can have the phase that the out of phase angle is 180 degrees, which is like the maximum opposition what can happen. And as you can see in this little diagram on the left hand side, I hope I can show that here. You can see that there's a influence of the out of phase angle and the amplitude of the voltage, and the out of phase voltage, of course, will determine how much the out of phase current will be. As you can see here in my two diagrams with the direct comparison, so it's the same set of machines, same set of system network. You have seen before the current constriction we have talked about. And we can clearly see that with the out of phase of only 90 degrees, smaller out of phase angle, you would have smaller fault current, of course, because the driving voltage is now smaller. However, on the other hand side, you can see that with the same system, we have at 180 degrees out of phase angle, the current constriction is now happening later. So the factor which, let's say, influences or dictates this behavior is largely in the machine parameters, time constants, reactances. Another point is because we are talking about full synchronization of generator and the grid. So that's why the grid data is also very important to get these kind of information. The reason, therefore, we will see that in the next 2 slides. And lastly, one very important, let's say, parameter which dictates this behavior is the inertia of the machine. The inertia of the machine, let's say, gives the system how fast or how slow the machine will, or let's say the whole system will interact in case of such kind of transient process. So generally speaking, if you have a smaller inertia, your system will react slower than if you have a, no, sorry, I'm mistaken that. If you have small inertia, then the system will react faster. Example, as in 90 degrees. If you have larger inertia, then your system will react slower, which can be seen, for example, here. The constriction will happen later. Concrete example, I will show you that in the next slide. So we talk about the reactances. So what we have found out is that the machine parameter between synchronous generator, conventional synchronous generator, and synchronous condenser does not have much differences. So relation are quite similar. The time constant are quite similar to that. The only difference they have here in this parameter is that the synchronous condenser of the same, let's say, power has very small reactances. So that's why if we have the same set of, let's say, the same apparent power of synchronous generator or synchronous condenser, the condenser always give a higher short circuit current level than a generator. So it might be that if you are, I don't know, asking for a solution, you said this is the same, it's a machine of the same power, but using a 2 different function, then it might be that for a synchronous condenser, a higher short circuit current rating might be required. Another point I have mentioned is the inertia of the system. So the synchronous generator itself, of course, you usually connected to a turbine and delivering that inertia of the system, what we need for the simulation. The synchronous condenser might not be connected to a turbine, but it can be connected to a flywheel to increase the inertia of the rotor stuff. So the value itself is, we cannot predict that. We have a data bank which can, let's say, assume a direction, how much I can assume for my simulation. However, to be sure, we might need the real data sheet to exactly simulate the case. And why is it so important to have these kind of information I will show you right now in the feasibility study we have. So you've seen 3 different simulations here. It is of the reapplication we have seen. We have, from one of our cases we have delivered. So the data is from the generator and from the transformer is coming from data sheets we have received from our customer, from our clients. So in this diagram, you can see that is the simulation have been done with the given information, like given data from the data sheet. So our focus right now is on the inertia. And what have been done is we have reduced the inertia from the data sheet now by 50%. And as you remember, I told you by reducing the inertia, so with smaller inertia, that means the system will react earlier or faster on changes, on transient processes. So you can see that now the current constriction is now here, and so we'll be reducing the inertia. We have moved this current constriction to the front. And the same set of machine, same set of data is now being used to simulate that case. But right now, we increase this inertia by 50%. And right now, you can see that the constriction is now moving to a later point of time. What does it mean for the circuit breaker itself? Now we have simulated that in cooperation with the arc voltage of the circuit breaker. You can see that the arcing time right now, you remember the case I mentioned with the voltage maximum to generate the maximum arcing time. So standard case have been simulated here. And of course, that has been always, these values you can see here is tested for our product. And you can see that for such a case, even though we have the construction now earlier, but you can open that always earlier. So that means the arcing time now can be smaller as well. And right now, if I would go back, you can see the curve that's even the constriction is later, but we are opening right now here. And at the point of the contact separation of the breaker, there is no constriction at all. So that's why it doesn't have any effect on the breaker. So you can see that same set of system data, depending on which data is being used and how much the modification has been done, we get 3 different results. So a generic, let's say, statement about vacuum not being suitable to use for out-of-phase case or synchronous condenser is not true. So that's why, but still we need your input. I need a complete set of data and all the information I need to exactly simulate these kind of cases, because you see that by modifying one of the facts, let's say one of the factor, we get different results as well. So inertia is only one part or one factor which determines the behavior in case of out of phase. Another point of what I mentioned is because we have an interaction between generator and the system. So the system data are also crucial to have. So you remember my green diagram is how it looks like with the real given data. And what we can do is we can change the input data, like the grid X2R ratio, the transformer X2R ratio. Of course, the short circuit capability from the grid does have an influence here right now. And of course, the high voltage level. So all of that facts have been implemented. And as you can see that by changing one of the factor, we can have either negative or positive results. It's very, it's a large number of variants which we can get. So I can only emphasize, please, if you want to have an, let's say, recommendation, a solid recommendation, we need the solid input to get any recommendation out of that. All right, so actually I've been at the end of my presentation already. So what I want to give you, the audience for today, is feasibility study have been made, and this is required to confirm the suitability of our VGCB for synchronous application. You have seen that short circuit current calculation have been included, and of course for the out-of-phase case, we have seen that synchronous condenser have a lower reactances, so it's often that the short circuit current level is higher. Also, the operating points itself of the machine does have an effect on the short circuit current level. Either you have higher current or you have higher asymmetry, depending on which operating points we are working with. You have seen also that the fault current due to fault synchronization, depending on the input data, might have very critical or not critical results at all. So it's very strongly depending on the input data. And of course, we have seen with our studies with different set of machines and system that the impact of inertia is quite significant for the interaction between the generator and the system. So that is what I can give to you. In case of any question for later or more details consulting, just reach me after the session.
Thank you, Hong. Yeah, really valuable once again. Thanks a lot. Yeah, I think we already linked your LinkedIn account to the registration here. And so people will probably find a way to contact you. And let's see, we've glimpsed a bit into the questions that had already been there. And to be honest, I do not remember which was the one you wanted to start with.
Something with out of phase, I think.
Oh yes, then I've see it. So it's coming from CH. Are you able to enlighten us on out of phase situations, and does the vacuum interrupters have challenges here?
I think I just mentioned that
Me too, yeah.
a lot in a lot
Yeah.
of slides. So yes, we did that, and vacuum is applicable for that. We need therefore then, as I said, the detailed study. But yeah.
Yeah. Thanks. I think it was, I've seen that, and it even enlightened me. So, oh, now I know what OOP is. So thanks for that. And the next question is a bit in the same direction. So we have twice the question, what is the best? Is it vacuum or SF6 for this kind of application? I mean, from what I tell on exhibitions, get rid out of SF6, but you know it from a technical perspective, I think.
How can I do? What I can only say that either SF6 or vacuum or oil or whatever circuit breaker or GCV, we all have to face or to pass the test, the type test mentioned by the standards. So at the end, it's the customer to decide what advantages he wants to have with which solution. But I can only say that our products with vacuum fulfill the same standard requirements as our colleagues from SF6.
Okay, yeah. So no matter what the isolation gas is, the type test is successfully performed.
Yep,
and
exactly.
Yeah, so go with kind of what you want and think of nature, I think. And next question came from PC. Is there any standard needed to comply with in order to ensure that the circuit breaker is able to perform the synchronization?
Yes, if I understand this question correctly. I don't know about any standards defining how to perform synchronization, but I can only say that for a circuit breaker like GCB, like generator circuit breaker itself, there is this IEC IEEE standard. They say if the circuit breaker is intended to use for synchronization, then you have to fulfill these kind of requirements. So I can only say standard says we as a manufacturer have to fulfill these kind of requirements, and that's what we do. So yes,
we do.
There is a standard.
There is a standard, and we comply with it.
We comply with the standard, exactly.
And I think the next one I see in the list here from FT for this 4.5 MVA step-up transformer settings, are we considering a different model of JCB? I think Fabian touched that already in his answer. We need a simulation there to check which would be the perfect model, because the one we consider here going up to 15 mega MVA, that's a different liga, I'd say.
I can only mention, or let's say emphasize, that each generator looks different. So it can be that for one 4.5 MVA generator from, I don't know, from this one manufacturer shows very critical behavior, but for the other one is easier. So we cannot say in general. So the best thing is to do some kind of simulation showing the real behavior. You've seen that this delay current zero and all of that. Yeah.
Always close the loop to the simulation, right? Then you're on the safe side on the dimensioning. That's one of my key takeaways, I think. And I think you already mentioned something like the X to R ratio, but is there, DS wants to know, is there a threshold associated with employing generator circuit breakers such as X to R or fault level?
Okay, so the fault level is free defined by the manufacturer. We can say we have a GCB with 10 KA or 40 or 25, whatever. That is free to the manufacturer to define. But the X to R ratio is given by the standard, and we have to comply. And as I mentioned in my presentation, the time constant is 133 milliseconds, and you guys have to recalculate it into the X to R ratio. I think there is a equation in my slide with the arc voltage where I give T and X and R. So you might use that as an equation.
And you can make use of that because, as we already mentioned, you will get access to the presentation afterwards. So, question came in from VP somewhere during the presentation. I think VP wanted to know what is the percentage of direct current breaking current in the generator circuit breaker?
Okay, I think for our product is more than 65%. I don't remember exactly, but the basic of that is the time constant. You have to test your circuit breaker, and depending on what is the time of contact separation, you either had I don't know, 65 or 70, 75%. So we definitely have more than 65%, that I can tell you. And depending on what the product you are using, we have a bunch of portfolio and different types of breaker. I do not remember them all.
Okay, yeah. Maybe we can put in some examples during
I think we have a catalog
written
or
answer.
some data sheet we can share.
Probably a link
or you
to
can
it.
go into our website. I think we have a website. Maybe we can share that afterwards as well.
Yeah, we do.
Yeah,
I think it's probably also part of the presentation, right?
Yeah.
So next one coming from ETO. Regarding the installation of the generator circuit breaker, do you need to use a metal frame, or can it be mounted directly onto a wall or floor? Is that something we want to take to Edouard?
Yes, of course, Edouard can answer. But what I can give in advance is it's depending on the on your installation at site and what product you use. But we are quite flexible.
Yeah,
we have a team dealing with that, so we can actually do everything.
Yeah, and you'll see an answer to that later on. There are some examples there. So once again, stay tuned. It's worth the time, I think. So let's see. I think for now we go with one last question and take the rest for the questioning round after Eduard's presentation. But one more directly to you, and I'll see you later once again for questions. So NB is asking, I'm learning about the power plant generation protection for ABC stator and all electrical protection for the electrical size settings for the
I think it's a comment.
It's a comment.
Yeah.
Oh yeah.
Thank you.
It's not a question. Perfect.
He's learning about.
Yeah,
okay,
it's
thanks.
learning. Okay, and then we take one last question, short answer. Where's the factory of the HB1C?
It's made in Germany, and I don't know how much I would talk about that, but that's Eduard's part.
Yeah, I think so. So we mentioned Eduard quite a few times right now. He will join us here on stage in a few minutes. I think we will have one more bio break, and let's take it for at least 5 to 7 minutes just to give you time for a coffee and whatever you need. I think there might be even somebody out there who need a cigarette or something like this. But take your time. I think we talk about 7 to 8 minutes, and you will see the timer then. So see you in a few minutes once again. Thank you, Hong, so far. We'll see each other again for the final question and answers round after Eduard's presentation. So stay on the line. We'll continue with the presentation of the HBC1.
Which one?
HB1C. Oh, yes, there I know. I need some coffee in a few minutes. So see you soon.
It's okay?
Okay, so welcome back. I think so. We will continue the journey through this webinar, talking on the HB1C. Now it's in the correct order. And I think by now, since we placed so many questions, oh, that's one topic for Edouard. You are curious to have him on stage. So yeah. Please come in, join me, Edouard. It's now your turn and presenting or introducing the generator circuit breaker HB1C itself. The stage is yours. Yes, you will.
Thank you all for being there, still with us. Nice two first webinars. As said by Michaela, I'm here today to introduce you to the new HB1C GCB. So this is before starting, just to guide you through what will be my slides today, what will be the content of my slides, so you can have some kind of overview where I'm trying to bring you in to go the journey with me. So at first, I will just give you a quick overview what Siemens is doing in the, let's say, in the work in the field of GCB, much more on the side of the product rather than the side of the technology, because this item has been already introduced by my two colleagues, Fabian and Hong. Then I will introduce much more in detail, let's say, the performance and the unique selling point or the unique features I would assume that our HB1 have to bring to the market. And then especially as the HB1C is aiming to the retrofit and replacement market, I will guide you through two business cases where our HB1C was kind of best solution, best answers for the concern of our, let's say, partners. And then finally, wrapping up the session with some kind of key takeaways that I would like you to take with you when we are closing this webinar. But first, before starting about the product itself, I would like to bring myself quickly so you know more about me. So my name, as you can see here, is Edouard Desplanches. I'm responsible so far in Siemens about the generator circuit breakers portfolio, meaning that my duty is to be sure that the product we are delivering to the market or we are offering to the market is matching the market requirement, whether it's in terms of performance, in terms of quality, or in terms of lead time delivery, for example. So it's very important for us at Siemens to have a portfolio which is quite consistent and offering the most of our own technology, which I will come up later on, to the customers. In these specific fields of generator circuit breaker application, I'm working in this field around like 16 years in various positions, starting from sales to BD and now as a portfolio manager. So I'm quite happy to be there in front of you today to introduce and speak with you about our HB1C. And please feel free to ask as many questions as you want about the breaker itself. It was a pleasure for us to introduce this breaker at NLIT last year. We had already kind of a good feedback and direct interaction with our possible customers and people interested in the development. And being there today, again, it's a way for me to open once more the discussion with you. So please feel free to ask as many questions as you have. Okay, before stepping in the HB1C and a particular part of our portfolio, I would like to bring few, let's say, background of Siemens generator circuit breaker story and where we come from, where we are. So the vacuum interruption in Siemens, it's a very well-known and proved technology. Siemens itself is using vacuum interruption technology, has a generator circuit breakers or within generator circuit breakers since more than 40 years. So it's a well-proven technology for us, which is widely accepted on the market nowadays, mainly from the medium voltage systems. If you look at all the GIS or AIS medium voltage switchgear, you will see that vacuum is almost covering 95% of the technology used, and using it in GCBs and makes a lot of sense. This is also reflected by, as you can see, our install base. So more or less, I would say, as Hong mentioned, we have almost 4,000, let's say 3,800 GCB installed worldwide in various countries, which are currently protecting almost 80 gigawatts of power production. So that's really also proving how strong in our install base and how much of, let's say, partnership are we getting with our customers, let's say. Then on the other side, as you will see, I will introduce the portfolio we have. We are already having a portfolio which is standardized as much as we can, really trying to compete on the market to bring also a competitive solution, not only on the performance to the market, but also it's important for us to be able to customize the product we have. So we are really matching all customers' demand. And especially for that, I mentioned here in this slide that we have almost every year, we are delivering almost 500 customized solutions to the market, really supporting our customers to define as much as we can and support them as much as we can in their challenge, which is how they can protect their very important asset as much as they want. A very important part where we come about speaking about vacuum technology is the OPEX saving. So I will come back later on during the presentation, but one of the main aspects of using vacuum technology coupled with full spring drive mechanism is really to be able to provide to our customers a solution which is maintenance-free over the lifetime. And by being maintenance-free, it's really helps them to reduce their operational expenditures or their maintenance requirement. And what you can see from this slide here is we are also doing the same as Hong and Fabian are doing on the short circuit simulation. We are also running some life cycle cost estimation or simulation, trying to compare what are the savings our customers can expect by using vacuum and full spring over different quenching technology. And these values and figures of 75% is like an average for us. Again, here, if you have any requirement or any needs for us to support you in this direction, to say, okay, if I go with Siemens, what would be my benefit? That's where we can also answer you further than just on the technical side with short circuit simulation. And the last 2 points I will come on with is digitalization. So being a part of the big Siemens family here, of course, we are trying to use the best product from our colleagues, and CProtec and AssetGuard are 2 major, let's say, piece of protection and protection relay, which is used widely worldwide. So we are also, of course, integrating those digitization devices within our GCB. On one side, to use them as a live condition monitoring system, which is allowing our customers to access on real time what is the health index or the status of their GCB. And on the other side, we are also pushing this forwards to also going much more into the protection scheme and trying to include the GCB as a smart piece of equipment within the power plant. And the last point, before going further with the HB1C itself, is the vacuum technology. So as most of you knows, I would say vacuum is always coming from the medium voltage, and most of the colleagues on the market are providing vacuum technology up to 63, sometimes 72 kA, sometimes 75 kA. But I would say today at Siemens, we are very proud to have been able in the past to, let's say, push it to one of the most performant vacuum technology, vacuum interrupters we have today. And this today is under 10 kA. And that's also showing to the market that this technology can do even more. We believe in this one, and we are already also continuing development to prove to the market that vacuum is the best way we can, or best technology we want to use for generator application. So without further ado, I speak quickly about what are we doing Siemens on the market of generator circuit breakers. Let's have a look on the HB1C. And before going on the HB1C, I would like to introduce you to our portfolio, because we had our colleagues earlier speaking about what is a GCB, how this GCB has to fulfill some specific standard requirement due to its location and vicinity close to the generators. Then we had Hong speaking about some new application where we are quite successful together with some partners to sell this GCB on the market and installing them in synchronous condenser. But also it's important for me today to introduce you quickly what is our portfolio, because we are very proud of it, so it makes sense. Now, looking at the portfolio, as you can see here, we have a quite wide portfolio covering needs of power plants from, let's say, 50 megawatts per unit, if lower, up to 450 megawatts as a power plant. And if we translate that into some kind of rated nominal current and short-circuit breaking current, we see that we are able to cover needs in terms of rated nominal current up to 15,000 amps. And as I mentioned earlier, we have our vacuum interrupters, which is allowing us to break short-circuit current up to 110 kA. Of course, here being a part of the medium voltage application, we have rated voltage up to 24 kV. As you can see, we have a quite various range here of product coming from a withdrawable product with a very high LSC compatibilization to some very customized product as a VB1, which is a medium voltage cell switchgear, and also one of the flagship product we have today on the market, which is the HB3. So HB3 is made to be installed together with what we call IPB, so insulated phase bus, and for very high power plant rating up to 400 megawatts. But today, what makes sense for me to introduce, or why I'm here today, is to speak to you about the HB1C. As you can see here, the HB1C is what we call a GCB without enclosure, meaning that the main, let's say, market for the GCB is to be installed either in an MV cell or a medium voltage switchgear, or to be installed in a power plant directly in a room, which will be closed by fence or by door. But this will not come with any enclosure around it to protect him. Let's have a look deeper. So HB1C, what we speak when we mention about HB1C and the main performance. So as you can see here on the slides, an HB1C is made from, it's a system, it's a solution, it's not only a GCB or a component. So we are going from a component perspective, which is what was a generator circuit breakers, to a solution, which is more than just a GCB. As I will show you later on, this HB1C is made of a GCB, a line disconnectors, two earthing switch, but also together with a frame steel support, you can see here, some cables from the GCB, which are connecting those, the GCB function to the control panel. And what we are calling today an HB1C is this complete solution we are delivering, let's say, has a kind of turnkey to our customers, where we have the braking component, we have the steel frame structures, which can help then the equipment to be installed either directly on the floor or on the wall. I remember it was one of the questions we had earlier in the chat. And then from this component or this active part of the solution, we have to connect them to, let's say, the brain of the solution, which is then the local control cabinet. And this is overall the solution we are delivering to the market. Looking at the performance, here, as I mentioned, we speak about GCB rated up to 24 kV, medium voltage solution. We have up to 6.7 thousand amps as a rated nominal current at 50 Hertz. We have also braking capabilities up to 72 kA with a withstand of 3 seconds. What makes this HB1C unique, and that will be, you will hear me saying that a lot in the coming slide, is the flexibility of the product. So we have designed this product with having in mind the retrofit market. Our wish was to bring to the market something that no one did before, meaning that we wanted to bring something which was flexible and will support our customers to replace their aging, outdated GCB with something new, and they will get more. But also having in mind that when it comes to a power plant, you don't want to come to the power plant and disrupt too much the power plant, whether it's time needed to do the replacement, or if it's to change and adjust the bus bar routing or the room size. You want to be able to fit in with minor, not to say no modification. And that's why I will go back to these 2 points when we called our GCB HB1C, which has different type of configuration, whether we call it L shape or I shape, and I will come to this point right after. And also in terms of installation, so this HB1C can be installed either in the horizontal version, as you can see here on the slide, or it can also installed directly on the wall or with its own frame structures. Of course, we are following the dual logo standard, which has been introduced by Fabian earlier. And again, just to give you some more, let's say, background, where we come from, why we believe in this equipment, and why also we get some very good feedback from the market developing this equipment. It was because of what you have in front of you. So what we have in front of you is whenever whether you are NPC manufacturers, whether you have this at site, whenever in the past you wanted to have not only a generator circuit breakers, but you want to have some more equipment together with this one. So let's speak about a main disconnectors or a line disconnectors in line with your GCB, which will allow like a visual disconnection. Because when the GCB is open, whether you speak about minimum oil, whether you speak about air blast, whether you speak about vacuum or SF6 ones, you cannot access directly visually that the contact within the arcing chamber are open. And how you do this, how you can prove to your maintenance team which will work on the generators that the contacts are physically open. One of the good way of doing this is to incorporate in your main current path these line disconnectors. That's the blue part we can see today on the slide. So when you want to incorporate these line disconnectors, then you have to buy, or in the past, you had to buy a separate equipment and connect it with your GCB. And you see here between the generator circuit breakers, which is shown in red, and the disconnectors, which is shown in blue, you have some extra piece of bus bar, which is this inclination bus bar we have here. Or it could be also flexible breadth connection. And then you will also see that on both sides of the disconnectors and the GCB, we have what we are calling earthing switch. Again, here it's all related to personal safety outside, that whenever you have someone working to prevent any fault or issue with personal safety, you want to get your main current path grounded. This will preserve your personal working on the live path or being approached by the voltage. Again, here in the past, if you had or if you have a wish to incorporate such kind of devices, you will have no other choice than to purchase them as a standalone component and try outside to connect them properly. And as you can see from this picture here, and maybe later on much more visual for you when you will be able to compare it with the HB1C, is all these components are standalone. And in the past, they could also be all type tested based on their own standard, let's say. And today we were also trying to change that to say, well, we are saying these components are all installed into a kind of GCB application, GCB system. It should mean that we should try to test them all together to be sure that they are all working properly whenever they are interconnected together. So that's what we have done, always in the mind of trying to get it more compact, get it more efficient, I would say, in terms of material, because there also is a point of how can we let's say, optimize the material we are using and delivering to customers. So here, have a look here on what we had in the past and what the HB1C we think is solving. So changing or moving, I would say, from a standalone approach to a highly integrated approach. So what we have done here, as you can see, we took all the different components, which were before standalone, and we tried to mount them around the heart of the system or the center part, which is in our case, the generator circuit breakers. We are used to call 3H87, which is one of the flagship components we have on our range, which is, again, bringing and delivering a lot of benefits to our customers. So around this heart, we bring directly on the terminals disconnectors, and then again, integrating the earthing switch. And as you can see, the concept we come with is almost saving a third of the length, maybe a bit less than a third, I'd say a quarter of the length, which is then even more compact. We are now also being able to get rid or avoid the use of interface busbar between each and every different component, and they are all mounted on the same structures. Let's call it a module. One of the advantage we also believe is this equipment you are seeing today, HB1C, has been type tested together. So all the short time current, all the dielectric resistance are all being type tested with this equipment. So you don't have to look left and right to find the right type test for this different equipment. Here you have one equipment which is type tested together, which is of course assembled and routine tested together with a command control panel. So it's a kind of all-in-one solution, bringing, I would say, the most of each and every part. And I just mentioned that we use this type of module assembly. So we use that before in the past for HB3C equipment. I invite you to look also on a web page for the HB3C. We have a kind of configuration tool which can also help you to better understand the HB3C. We have this approach at Siemens to develop the module approach, because for us, it's bringing into a system all the advantage of having different system, different performance. So what is now mentioned is as a module, it's a part nowadays of the definition you can find in the dual logo standard. I took here the opportunity to copy paste it from the standard, what the module assembly definition is. On Siemens side, what we see or what we want to bring to the market as benefit for the module, call it module, is that as all components, disconnectors, earthing switch, and GCB are interconnected together, are integrated on the same function, are all type tested and routine tested together. This is really a way for us to provide to the market, again, with some very high level of reliability, but also, of course, getting it more compact and getting, let's say, getting less material. So always better in terms of footprint of the market, or the CO2 footprint on the market. This said, I will now step in much further in terms of technical performance and also having some focus on why we believe in vacuum technology and why we believe also that this HB1C, when we have vacuum technology coupled or together with a spring mechanism as a GCB, is really helping you to be more efficient on your power plant and keeping track of your OPEX, or at least reducing them drastically. And before doing that, of course, I would like to introduce you about the different configurations. So I mentioned earlier that we have different type of configuration for the HB1C, trying to fine-tune them about the existing and legacy equipment. So what we have done before designing the HB1C, we looked at all the different type of GCB which were installed on the market since the 70s till now. And we tried to make it that our HB1C has to be designed to be smaller than equipment, meaning that we want to be able 100% to fit in the existing footprint of your power plant without having to modify it. And to do so, we also realized that by playing with some kind of configuration, some kind of physical arrangement of our HB1C, we will be able to support this. So you will see here what I'm showing is what we are calling the I shape, and I refer to this all along the way to my presentation. I shape meaning that you have in the same axis the generators, circuit breaker, and the line disconnectors. So that's what you can see here. In the same axis, the x-axis, you have your GCB and your line disconnectors. And then on both sides, we have the earthing switch. So here in this configuration, we have the I shape, which is then installed on the frame for horizontal installation. Of course, as I mentioned earlier, we have two different types of installation. One is, as mentioned here, horizontal, but we also can use this HB1C vertically. That's kind of very useful when we speak about hydropower plant, when we have the generators at the bottom of the cavern, and we have all the or IPB going up to the JSUT, generator transformers, and then we have to either implement or replace a GCB. Then we can use this vertical installation, trying to avoid to have the bus bar going with some elbows and C-shaped bus bar to recover the fact that some GCB are not able to be installed vertically. That's also there's some kind of benefit going with vacuum. I will come back on this later. And as I mentioned, so again, here we have an I shape. The reason why we have, again, in the same axis, the GCB and the line disconnectors. So here, in that case, we have an I shape installed vertically. But as I mentioned, we have also the L shape. So the L shape is here. And as you can see, we have a 90-degree angle between the GCB and the disconnectors. And this L shape is really made to be able to fit the size. The footprint is lower. We also have in some existing power plants the bus bar coming from the top, leaving from the top. So having an L shape was really a way for us to continue supporting the customer to say, okay, how can we replace existing breaker by a module which comes not only with a GCB, but with extra function, but still fitting in the existing footprint, meaning minimum disruption at site, whether it's a time of effort of changing. And that's today our answer. Then when we look at the performance of the GCB, so as I mentioned here, the GCB we are using, which is really the part where my colleagues were speaking a lot about this today, we are using it, you can find it on internet, it's called the 3AH37, that's really the core, the heart of our HB1C, which is a well-proven technology. I will answer also one question here. So the vacuum interrupters, the drive mechanism, the GCB, the main part is all made from Berlin, Germany. And that's also something we are very proud of. So all my colleagues here and myself included, we are sitting in the factory. So this equipment is really like the babies of the colleague. We are all kind of big family trying to deliver this to the market. And that's also why we are always trying to fine-tune it. So we really very proud of what we're delivering to the market. So quickly, here's the performance. I think earlier today was some question about the DC components. So you can see it here, 70% for the system source fault, which is quite impressive and of course type tested. And before jumping to the mechanical part of the GCB, I would like to have a short stop on the vacuum interrupters. So what makes a huge difference, I would say, between us on the market when it comes to such performance is the vacuum technology. If you are used to deal with generator circuit breakers, you will see that in the past we had some steps in the technology which were used on the power plant. I would say everything started in the 60s, 70s with air blast technology, which was coupled also with pneumatic drive mechanism. Then we moved from air blast to some case minimum oils, then from minimum oils to some case SF6, and I would say today from SF6 to more sustainable solution, in one case which could be vacuum interrupters. And as you can see here, we're not using vacuum interrupters just to be more sustainable. We are using vacuum interrupters because it brings to our customers a lot of advantage. One of them is being the maintenance-free approach. VI vacuum interrupters, as a short, has been proven to being sealed for lifetime. We don't have any moving component. We don't have any seals inside, which we wear and create some leakage. It's sealed for lifetime, meaning whatever our customers get and delivered by us, it will be maintenance-free until the end of lifetime. And when we say maintenance-free, this is also linked to what we are calling the mean time to failure. So today we have a mean time to failure on our vacuum interrupters up to 83,000 years, meaning that that's a proof, or let's say a seal of quality to say whatever equipment you get from us, you get from Siemens. When it comes to arcing chamber, which is one of the most, let's say, precise, sensitive element in the GCB, we at Siemens are giving you one of the most reliable solutions, one of the most sturdy, durable solutions on the market, and this MTTF is really a proof of it. And on the top, about the maintenance-free solution, so when we say maintenance-free, it's just like, it's maintenance-free until it's not anymore. So meaning that we are able not only to give it maintenance-free, but also to provide you with a very high durability. And this durability here is mentioned at the bottom. So with the vacuum interrupters, we are able to interrupt the full rated current 10,000 times, which is almost, I would say, if I compare to others today, it's almost 10 times more. So when we go with offering vacuum interrupters, it's because it brings to the market the most durable and the most reliable sturdy solution we can find. And that's also why we are still continuing and not changing, I would say, our IC development to go from vacuum to some other technology. It's really, we believe in vacuum and we think it's also bring to the market what the market expects, especially when it comes to maintenance-free. Now, having a look on the breaker. So the circuit breakers is made of two things. On one side, the arcing chamber. On the other side, the drive mechanism. I think I just mentioned about the vacuum interrupters, which is there to open and clear the fault, but without a drive mechanism, it will not do anything. As you can see here, I will just show this one. So M3, yes. So as mentioned by Fabian, we have type tested equipment based on the latest standard. We are able to bring to the market one of the most durable equipment, not only in terms of mechanical opening. So when I said these vacuum interrupters can interrupt 10,000 times the rated current, sorry. Then I'm really here to speak about the contact system and the bottle itself. But again, if you want to be able to open this contact system 10,000 times, you have to get the mechanical linkage and the drive mechanism, which also push and operates these vacuum interrupters. And for us, of course, it was very important to select and to use the most durable, sturdy, reliable, how we want to call it, a drive mechanism. And for that, we were helped, let's say, by the SIGRE. So what we have done and what Siemens is doing since years, we are developing our own full spring drive mechanism. Today, the HB1C has the complete range of circuit breakers, generator circuit breakers we have. They are all equipped with full spring drive mechanism. The reason why we are doing this, it's again to bring this level of durability and sturdiness to the market. We want to bring an equipment, and GCB, I think my colleague mentioned, but GCB is always seen by our power plant owners, by maintenance team, as a kind of insurance for your power plant. And you want your insurance to work at any time. And you want your insurance to be reliable. And as such, when it comes to a GCB, you want to be sure that the GCB, anytime you need it, whether it's for opening or closing synchronization or opening on fault condition, you want it to operate properly and to clear the fault, if any. And to operate properly, you need to get, of course, a good quenching method, but of course, a drive mechanism. Here, I mentioned here an extract of the SIGRE report you can find also on internet. Mainly what this final report is stating is that we can do some link between the reliability of high voltage circuit breakers, drive mechanism, and the generator circuit breakers, drive mechanism, because they are quite similar in terms of construction. And they are looking to say, well, if we look then about this big picture of the high voltage circuit breakers and GCB, we see that the major failures, what we call major failure, are always coming from the drive mechanism. And so it's really important to avoid major failures to select a drive mechanism which will minimize, or to a minimum, let's say, this possibility of failures. And while going through, the SIGRE went through the different reliability report of different manufacturers based on different type of drive mechanism. And I mean, you can mention it here. It's mentioned that they have a look on fruit springs, they have a look on pneumatic, I think, some hydromechanical. And what the SIGRE report is stating that when it comes to GCB, or even I think high voltage breakers, one of the most reliable way to operate this GCB and to minimize the major failures happening at your power plant is to use the full spring mechanism. And once more, that just emphasizes why we believe that coupling the vacuum interrupters or vacuum technology together with a drive mechanism is a way to deliver to our customers one of the most durable equipment to the market. So really focusing on what makes the heart of this HB1C, we again focus on what can we bring to customers which make a lot of sense and that our customers can use for the next 25, 30 years without worrying about it. So that was the view on the GCB. Now, quickly going through the disconnector. So as you can see here, I bring some data about the disconnectors. What you can see, which is quite important, is this insulating distance. So the rated voltage and rated power withstand voltage across insulating distance. Again, as here we were doing and initiating our own type test, we were able to fine tune and to select properly the disconnectors so it fulfills the requirement of the dual logo standard. That was very important for us. And again, here you can see the M3 durability class or endurance class on the disconnectors. And just to also explain you quickly how it closed. So in that case, here you have the disconnector in closed position. And whenever you want to do some maintenance or whenever you want to have this visual opening of the main current path, because on one side is a terminal, on the other side also, as you can see here, I cannot say whether my GCB, my arcing contact in my vacuum bottle are open or not. Could be they are open, could be they are closed. Visually, from this location, I cannot say. A good way to say it is to open the disconnector. Which brings me also to the earthing switch function. So here, earthing switch, again, I just want to use this slide. You will see the main performance. They are all summarized in our flyers. You can find in the download section of the webinar. Here, again, it's just to explain you quickly how we have this earthing switch coming. And here, for example, on this picture, what you can have is a kind of HB1C, which will be in its maintenance position for the generators, meaning that we have earthing switch which are bringing the current path to the ground, so people can work properly on the generators, for example, and disconnector open. So that was one point. Then I will quickly go through the main dimension. As I mentioned, that we will really, it was very important for us to have an equipment which was compact. So here you can have some very gross estimation of what is today the length, width, and height of our HB1C module in the I-shape condition. On the other side, what I want to emphasize that our GCB is full spring operating mechanism, but the disconnecting switch and the earthing switch are motor operated, and the location of the drive mechanism can be on either side of the module. It could be on the left side, looking from the generator side, on the right side. It's really up to customers to discuss with us and to find the best solution which will fit their needs. And of course, I have the same slide with the L-shape, with the same kind of flexibility. Again, here you see that the length is smaller. And again, here the aim was to bring this system to the market, being able to fulfill even more. Sorry for that. Then closing with some data. So I will try just to summarize quickly what we really want to bring, or what, if there was some, not yet the key takeaways, but some specificities and flexibilities we think, and we, I would say, today we experience also are the one where the market is coming to us. Is on one side, as I said, we are using this module assembly approach, which is now a part of the IEEE in its definition. How we see that as a benefit is mainly because when you are assembling all these components under what I call this workshop condition, it makes sure that it's much more interacted together much better than if you then only at site start to couple equipment together, interconnect equipment together. Then you are safe. All is type tested, all is routine tested, all is delivered as a solution with all equipment already integrated and interconnected together. On the other side, we want to bring flexibility. So it's a standard solution, yes, but it has to be flexible. Why it has to be flexible is because we don't have one old legacy GCB type to be replaced. So here we speak, as I mentioned before, we had in the past some air blast breakers, some minimum oil breakers, some SF6 breakers, which are now reaching the end of life. And it's up to us, Siemens, to provide the right equipment to the market so our customers are able to select from us an equipment, to customize it a little bit, and then to install it, let's say, peace of mind in their power plant, which also linked to get more. So what we were also thinking is, initially we could also thought, well, we have a FreeH37, which is a GCB as is. Why not to just use this GCB and not bother that much about adding more equipment around? We want to do this because of personal safety. We believe that even though in the past, the size of our equipment was much bigger than today, when we speak about GCB, when we speak about arcane chamber, in the past it was very bulky equipment. Today, with vacuum, we are able to be very small, very compact. I would say vacuum circuit breakers are one of the most compact on the market, especially when you look at the HB1C, the HB3C, or the FreeH37. And here, with an HB1C, what we are able to do, and I will come to that with the business case, is we are able to replace an old, I would say, single function equipment, like old generator circuit breakers, which was only, already a lot of things, but clearing the fault, and installed in the same footprint a fully equipped system, meaning that you have a GCB, you have a disconnecting switch, and two earthing switch, meaning that you are improving your safety level to normal, let's say, today's standard. And that's kind of priceless for customers which are looking for how I can work better. So I don't have to do the earthing switch manually. I can only operate the motors. This is all interlocked together. So that really help our customers to work safer, I would say. I mentioned earlier, we are maintenance free. I can go further on that, I think, for hours, but really here, what the main point is we are not maintenance free for being maintenance free. We are maintenance free because it helps our customers to save money. So this is really the point here at Siemens, and that's also why on the top of making some short circuit simulation, we are doing this lifecycle cost approach, which is ready to show you that based on your own equipment, based on your own operating condition, that's where I think that's the kind of money we can save you over the next 20, 25 years if you go with vacuum. Then one-to-one interface, as I mentioned, we are doing standard equipment, but we are always customizing them so they fit perfectly at site, meaning that we want to come to a very small distribution at site, not changing equipment, so we can come with our solution and install it directly. A bolt-on approach is very important for us. So when we are mixing both, or we are developing both like one-to-one interface with bolt-on approach, it means, and you will see it in the business case, that we are able to take the old GCB out and bring the new GCB in with almost no modification on the middle voltage, meaning that the bus bar, the flexible breads, the footprint on the ground will remain the same. You just have to take the old GCB out, put the new one, and you are able to, let's say, I will not tell them enjoy, but you can get more with this declinking switch and earthing switch. Of course, as mentioned, we wanted to be able to supply all this equipment together to fine-tune the interlocking approach, meaning that all the equipment will be delivered on the module, will be interlocked together. And last but not least is, of course, the F-gas-free systems. Nowadays, we have much more stress, I would say, on the F-gas worldwide. And this is even more true in Europe when we have some new regulation coming, which is today is not extended to the GCD application. It will be soon there for the medium voltage application, whether we speak about primary GIS or secondary GIS switchgear. And we don't know what the futures will be. And that's also why, on the top of having this impact in terms of CO2 footprint with the SF6, we believe that going to the market with some kind of F-gas-free solution is really the right way to make it. So that was also very important for us at Siemens to emphasize this point. So this was mainly it when it comes to the product. And I will take the next, I think, 4th slide to drive you through a very quick business case. So what we call retrofit. So quickly before starting with the retrofit, just to have the common understanding, so we have a common ground to discuss together later on, I will say, is what we are calling retrofit. So retrofit or replacement is or implementation is just like you have an existing power plant, you have an existing switchgear, and you want to replace or you want to improve some equipment. And by doing so, you are increasing your performance, reducing your OPEX, and so on and so forth. So that's where we think HV1C is quite powerful. And I will show you that with a first example. So in this first example, we have been asked by customers to provide some kind of solution to replace an old air blast breaker. This breaker was installed almost more than 30 years ago. And as you can see here, we have, let's say, get some feedback from customers. Why do you want to change it? What's the hurdles you are facing with? And he said that, well, so equipment is now aging quite a lot. So every day which is passing, it's elevated risk of malfunction, of issue coming with this. I have maintenance costs which are now rising up. And also what was important for them is that they are very hard time to understand what the futures will be. How can I access spare parts? How can I access technical expertise, which will help me to solve some issue on my breaker? So locally, the maintenance team was able to do some specific basic maintenance on the breaker, but they were not able to solve issue if those issues were coming. And GCB, being in the current path of the generators to the GSUT, if your GCB is not working, then our customers are not able to deliver the energy to the grid. So it's a loss of revenue for our customers, but most, let's say, it could be also very tricky for the grid. So Hong mentioned about synchronous condensers. So nowadays we have some grids which are really stressed about having some fluctuating loads on the grid and poor generation. So it's very important for our customers to have to be able to produce energy whenever they are asked. And having an old GCB is sometimes too much risky for them. So when the customers came to us, as you can see here, he had only a GCB outside with a disconnectors on the top right corner of the MV cell. So say, okay, Siemens, what can you do for me? Is there any ways you can have a solution which will improve my performance and reduce my risk? And also anything else, you let me know. So we came up with this solution. As you can see here, it's not only a HV1C, it's a HV1C plus. So that's where we are very good at is how from a standard solution, we can extend this solution to make it fitting to our customers. What you can see here, it's a HV1C on some kind of skid, which is the blue part, which is supporting the HV1C to have it at the same level as the existing, let's say, busbar interface. And then the issue we're facing also is, well, our HV1C was too small. It's like, I mean, I like to have this kind of issue rather than too big because at least we fit in. And here what we have done to go from the HV1C terminals to connect all new GCB terminals to the existing power plant, we use what we are seeing here in orange, this interface busbar. And then to be able to be, as I mentioned, a one-to-one interface, like you take the old one, you put the new one, we have managed to create these terminals, which were at the exact same location and dimension as the old one. So meaning that for our customers, what he will get is a complete turnkey solution where he can get his old GCB out and put our new GCB in. He will be even able to reuse the flexible connection. Meaning that when you have this kind of solution outside, it's already minimum site disruption. You are also improving your time for replacing the equipment. You are also, let's say, not modifying your existing components. So that's also very important for our customers. When they have some type-tested MV cell, type-tested switchgear, they want to have a minimum modification so they can still have their certification on some other regulation which could apply. And that's also important for us. So the minimum modification we have, the better it is for our customers. And then it all comes to benefit for our customers. Less outage time, so I can do this modification faster. I can also use similar equipment for this cell to another one. I have a small GCB, it can fit almost everywhere. So that was really important for us to have this approach to customers, always looking at a one-to-one replacement. And then I have another example here, which is a draft here, which is coming to say we could also have what we are calling implementation. Implementation means you see on the picture on the right, we have on the top a bus bar running. Our customers having in the past only a line disconnectors, but he was willing to install a GCB. The main reason is he wants to be, let's say, responsible of connecting the GCB to the grid and not leaving that to the substation. By doing so, he was in need of having a GCB installed, but he was willing to keep the disconnecting function. It was very important for him to have a GCB, the disconnectors, and if possible, he will do the earthing say, by the motor. What we have done in that case, we came up with HB1C, as we are able to install it vertically. We mount it directly on the wall. You will have some connection on the top, some L shape of the bus bar, then on the right, and this GCB will be directly connected. And that's the kind of issue our customers was facing, that he was not able to find any solution to the market. And I would say that was a very good business case for us to say, well, that's good to see that when we design something and we bring it to the market is highly welcoming such initiative, such new design, not to say innovation, because that's really fitting a demand on the market. And we believe that more or less in each and every power plant, we could have a good system to provide our HB1C. And now it's time to go back to the takeaways. So again, time is running. So as a takeaway, again, I will emphasize even more that we have this HB1C with integrated solution. It's a way for us to bring to the market a very high level of personal safety. We want to improve the way our customers are working, on one side by improving the operational expenditures, but on the other side, really pushing on personal safety, how you are able to work in more better safety conditions. And having these systems where everything is type tested, routine tested together, interconnected together, and then delivered as a complete solution to the market is the way we are answering this concern. On the other side, as I said, we have also not to bring this equipment to the market and then asking our customers, okay, that's a good equipment, but you have to remove this wall or make this opening, or I cannot access to the final location. You have to widen the door. No, we want it to fit as a one-to-one with existing GCB. So our, let's say, specification for the design was, let's look at what has been installed in the power plant. Let's take the minimum dimension of different existing GCB, and we have to fit inside. And that's, I think, what we have successfully done together with Fabian. And on the last part, coming back to the low maintenance requirement, I emphasize already maintenance free. So we have this HB1C has most of our range, which is maintenance free. HB1C in the case is drive mechanism for 10,000 close operations together, coupled together with our VI interrupters. Again, here 10,000 times interrupt cycle at rated current. And just for, I would say, I hope it will not happen, but as you can see here, we have this 30 interruption at full short circuit current, meaning that the bottom we are using, we went to some type tests and we had some, not some fun, I will not say that, but we run some type tests having one bottle, experiencing to open 30 and even more times the short circuit current, just to prove, to show that, well, it's still working, it's still there. And when it comes to GCB, our vacuum technology is something you can count on. Yeah, that's mainly it for me. Michaela.
Great. Thanks a lot, Edouard. Yeah, that was kind of a, not a run through, but a lot of information in a short time frame. Thanks a lot. We have still a lot of questions. Yep. We have still some questions from the former presentations. That's why Ong and Fabian will join us again here on stage. But let's start with some question I think might be dedicated directly to you. And we take one that's already in for a while. It came from IP, and IP wants to know how free most circuit breakers can be utilized in Sahara in Africa.
How free?
So yeah,
okay.
Depending on the temperatures and surroundings, I think.
Get the point. So I would say today, some of the main challenge we have in the GCB is like we are always having to withstand a very high current. And when you have a high current going through copper or aluminum, it's react, and we have this what is this Joule formula, lost formula, which is I squared R, and so you have a lot of heat coming off the GCB. And as the GCB manufacturers, we have to type test this and to confirm to our customers that whatever the condition at site, this temperature rise, what we are calling temperature rise, will never go higher than the limit from the standard.
Okay.
And so what we are doing on our side is that we can speak about sub-Saharan tropical, let's say, condition, that it's on our side, again, to use a simulation, to use some type test performance to say, okay, if, for example, your ambient temperature is above 40 degrees, which is kind of 85% of the case is 40 degrees. If it's like 50 degrees, we have this most of the time in Middle East or in Africa. Then we have sometimes to apply derating on the current to bring this current down so we are not overheating the GCB. So that's one side of answering it. On the other side, when it comes to Sahara, I also think about dust. So that's where we have some equipment like the HB3, which is IP66, which prevent a very high level of protection against dust. And I will just take the opportunity that we mentioned about the tropical approach also to go on the other way to the Arctic. So we have done, I think it was last year, looking at my colleagues, 1 year ago, some webinars also about the Arctic condition.
Okay.
If we compare again air vacuum to some other components, so we don't have this liquefaction stage that some of our colleagues can face in SF6. So if you go too low in temperatures, SF6 will liquefy or gas will liquefy. As we have vacuum, we don't have this issue.
No problem.
So it's a perfect fit for us. So we are very pleased today to have a lot of our GCB which are installed up to -40.
Oh.
And that's also for us kind of selling point, which is very important for our customers because they can have our GCB installed outside -40 without any other protection than our own GCB.
Cool. Yeah, interesting to know. Then I see a lot of questions concerning rather, I think, the technology behind. So maybe we take that for later.
Yeah.
And let's jump directly to one of the newest questions that came in during your presentation. So yeah, I think the question from CO, right? The first one I see, the most new one is, can we install an HB1C near the sea? Yeah. I guess yes. Just
So as I mentioned, the HB1C is a GCB without enclosure, meaning that we don't have any metallic protection, which we prevent in with water ingress or something, or humidity. No, water ingress mainly, sorry. And this equipment is to be installed either in an MV cell or in a room at a power plant. Yeah. But also we are having some different equipment which will provide the HB1C together with a cell, which then can be IP54, IP66, and suitable to be installed in the sea. That's
okay. So we have different solutions there fitting for kind of every state. So is there a maximum operation altitude?
So the maximum operation, no. So again, here, as for the rated current, we have some derating from the standard, which define if we go higher, then we have to derate the maximum rated voltage. Again, nothing fancy for us. Yeah.
Thanks. So ambient requirements for mounting and operating, I mean, that's probably...
No, that's, I would say, that's no question. No. Again, we have some...
I mean, people might be able to work there, but
It's okay. So we have GCB installed everywhere, whether we have even on our side some application in ACFNS solution, which have very high temperatures, we are switching. We have some application in, as I mentioned, Arctic condition.
Yeah.
We are quite,
kind of everywhere suitable. And then you showed the retrofitting. So just take it and put it in. And AA wants to know, how long does it take to retrofit one generator circuit breaker in an existing panel, just to kind of estimate the shutdown time of the generator plant?
Again, that's the same answer as Hong and my colleagues. It really depends from one project to another. Sometimes I would say all customers seeing the GCB as a very critical asset in their power plant. They will say, I will not make the outage until my GCB is there and delivered, and then it all prepared. I would say it can vary from 4 days to 12 days as an average. Again, depending on very specific solution, depending on the kind of project management you will do upfront, and the way our customers want to be prepared.
Yeah.
But with this one-to-one solution, that's also a way of saying, maybe if we have numerous units at site, the first one will be the piloting phase, and then we can replicate this one quite faster. So it will really depend on who will doing the installation also, but as an average, I say between 4 to 12 days. That's a good average.
Rather fast, I think, because we're talking in a working environment with limited space and things.
Usually we have a maintenance team locally, which are also quite willing to support us and to make it happen. So the main point is, when it comes to retrofit, is really to have upfront work, which is there. That's why we are always doing site surveys. That's why we are always going there, meeting customers, taking the latest dimension. Today we have some 3D scanner solution which are here to avoid any mistake from the existing drawings. So I would say more and more the technology is there to support us to reduce the changing time.
That's true. Yeah, don't rely on plan. Just do the measuring, and it's so fast, and you get their image there. Cool. Yeah, great to see that. Then it's from FD. The earthing switch is made to 62.271.100, so the IEC there, and the vacuum circuit breaker is to a quite or a bit slightly different standard, so it's 73.013. the withstand voltages are different in these two standards.
Yep.
With
That's
higher
good.
than
I think that's
yeah.
that's a very
With, well,
true
let me take the
statement.
question.
I want to answer.
Yeah, with withstand voltage
that's-
should we use when we have two different values, so that the audience knows the question. You already
I
could
will
read
tease
that.
the audience, not answer
Yes.
directly. No. So that's the main advantage of having a module. And that's the main advantage of using the latest standard.
Mhm.
In the past, we have two different standards which could apply yes or no for the equipment when this equipment were used together with the GCB.
Mhm.
Today, going with a module, I can answer this question directly. You use the GCB standard because that's the one which is used for GCB module and system. And it's one, I'll say, not to use the term headache, but one more work for our customers or consultant company or engineers to think about, which one I have to use. No. This is time tested together, it's worked together. Look at the IEC IEEE standard, it's no compliant with.
Yeah, so just go the easy way and take the complete type tested system, right? Yeah, perfect. And then I think you already answered that, right? How many times can the HB1C interrupt on fault without maintenance?
30 times. Yeah.
And you said you already tested that and it was still working.
So, even more.
Right?
So
yeah,
we
perfect.
tested that too.
Yeah, that's why we guarantee 30 times, right? And the next question is, coming from DS, can the HB1C be used with pressurized IPBs?
So as such, the HB1C being without enclosure, it cannot be used directly as the one solution. What we can do is around the HB1C, bring it into some kind of MV cell, what we have today in our range, which then can be connected directly with IPVs. Yes, that's something which we work on our side, which was not a part of today's presentation, but that will come.
I mean, at least you know, right? And then contact. Oh, that's
yes. No.
Can contact wear for interrupters be estimated?
Yeah.
So in America, I need to advise Gerhard where to find that so that the auditorium can also read it. It's coming from DS, the question, and it starts. Be estimated in numerical protection relay or bay controller, or can it be measured or inspected somehow?
So that was one of the request we get from our customers from this break. I show that they also wanted to be able to have this live condition monitoring system installed on the old breaker, and they were not able to. So if I look at customers in the power plants, they are more and more used to have each and every critical asset being monitored on live conditions, so they can remotely access what's the health index, and even if the equipment is critical, I need to know exactly which work or not. Yes, today with vacuum, we have either the use of CProtect or Asset Guard to do this condition monitoring. And then we have a human interface, either from the web page or from the computers to access then what will be the health of my vacuum interrupters, and especially the contact system.
Yeah. And then AGD is curious, is there any video of the operation?
Which operation?
Maybe of the generator circuit breaker itself. I'm not sure. Well, of the moving operation of the retrofit.
I did not do some, but sure. Well, welcome to the factory. We are here in Berlin. We have one HB1C at Berlin, which can be shown and operated. So rather than doing on video, you're welcome to join us at the factory.
Perfect. So travel to Berlin, I'd say.
Nice city.
So, and next question also came in from AGD. The mechanical interlock, for example, with a castle key, and electrical interlock, is both possible?
Yeah, so today we have two main systems, I would say, of key interlock on the market. I don't know if I can mention them, but we have castle key, we have Kirk key, mainly for the North American market, and both of them has been already used, whether on the HB1C or different breakers. For us, it's we are using them quite usually because that's best practice for power plant owners who want to have, again, this level of safety, allowing customers to be very safe when it comes to operate equipment manually, so that you are not creating short circuit yourself.
That's normally not really healthy, I'd say. Thank you. And ER wants to know, how is the contact erosion measured?
So we are using
Yeah.
some very fancy formula. I will not
okay.
display too much
Okay.
today. Basically, what we are checking is when we are opening the breaker, we are estimating, we are getting the info from which type of current was there when we open, and when the current disappeared. So it will give us the current over the time, and then we just estimate how long it takes, and then we give the right answer. But that's
Sophisticated calculations behind, right?
not that much. It's kind of
Yeah.
widely used. I mean, it's widely
Okay.
known from all the medium-term switchgear. We are just there getting like using the fruit of our cooperation with the Ciprotech colleagues,
Yeah.
and that's really useful for us. Yes.
Use the data. Yeah. As always, data is the new gold.
Yeah,
I
exactly.
know. Yeah. And then let's see. CP wants to know for HB1C. You mentioned 179 kiloamperes dynamic current. What about the thermal current that becomes important for faults supplied from the generator, having a longer direct current part?
That's a lot of things in one sentence. I can
Yes.
answer the first part. I don't know about the
Okay.
last. For the thermal current, so we have many when we are testing some equipment, especially when it comes to short time current, STC. We have two parts, which is one is the dynamic part, which is mentioned here, which is 197 Ka peak, which is there to, I would say, check the breaker to check if mechanically things will be okay afterwards. So that's just to look whether the breaker is able to withstand the peak. So that's a mandatory type test, which is as per the. Then when it comes to my understanding of the thermal current is the 3 second. So what we are also doing on the same equipment, which has been used for the STC, we are running a 72 Ka short circuit current or igniting current for 3 seconds to see that if we have no damage and if you can open properly the breaker afterwards. So what the standard say, if you go with the short time current testing, once you pass the testing, you have to open the breaker to see everything is fine.
Okay.
And the last
Thanks a
part,
lot.
I'm sorry, I will have to check with the colleagues what's.
Yeah, let's get them here
I'm
on
not so sure.
stage
So
and
maybe
see
you can answer
if
it.
they
I
can
can.
already answer, or if this will be a question
The longer DC part,
that
I'm
we
sorry,
take kind of offline. Yeah, not nodding there. Nevertheless, come and join us on stage because,
Let's
you're
continue
still
together,
here.
huh?
Let's continue together. And now then we have to decide who will be the ones answering the question.
It's okay.
Okay, that's interesting. Do your breakers have switches for starters of gas turbines?
Oh, I can answer that. I like it. So,
Okay,
yes, so
perfect.
for gas turbines, the gas turbine has a very specific way of starting. You cannot just initiate the gas and expect the gas turbine to run.
Okay, yeah.
So you have to launch it first to initiate. And usually how the gas turbine power plant or owners are doing this is like they are using generators as a motor at first. And to use these generators as a motor, you have to inject current. And to do so, they're using what is so-called SFC, starting frequency switch, which is then connected via the GCB to the generators. So they inject current through the GCB. We have this switch available for most of our complex system. So HB3, HB1, VB1. I'm referring to the portfolio, but yes, we have. And also this switch, coming back to the synchronous condenser, are also used for synchronous condenser to initiate this rotation at first stage after maintenance. So that's a part of our solution, yes.
Perfect. Thanks a lot. So, and then I think it might be a question for Fabian, because ND wants to know, since when is the IEC IEEE 622 and so on standard, and this version 2021, since when is this version mandatory?
Yeah, good question. Thank you very much for that. When doing a type test after the new release of this version, we have to do this type test according to the new release, according to the new version. So when planning a type test, beginning of 2022, we also have to apply the new version of 2021. Simple as it is. As it is released, we have to take care for that in type testing.
Thank you. And so AA wants to know, by any chance, have you come across any query requesting to install harmonic filters inside the generator circuit breaker panel? And if yes, what was the reason?
I cannot recall any project where this
Okay.
has been requested. More and more what we see is what we call poor quality sensors. So again, coming back to the synchronous condenser, coming back to having a grid, a network which is clean and able to have the right frequency or right quality of power, we have been more and more involved in having power quality equipment installed in the GCB, monitoring this, but so far I never heard what that is.
Me neither. I think I don't remember that. No.
Okay.
So we can ask
So,
our colleagues
not
further,
yet.
but so far no.
Not yet. Okay, so we don't have a reason for it because it was not yet there. So, and then GSUT is mentioned in this question from DOH. So I think it's a question to Fabian again, maybe. Let's see, DOH, as it was previously stated, the GSUT is usually connected very close to the generator circuit breaker. Using vacuum technology in the Siemens generator circuit breaker, yes, we learned about that. Does this have effect on the temporary overvoltage and TRV during switching? And has there been any consideration for the generator circuit breaker design? Or is this a problem for the power plant designer to consider when selecting surge arresters? Just move it somewhere?
I actually guess this question is coming from the history or based on the history.
Oh, okay.
Because when we are talking about vacuum interrupting technology, there was always a phenomenon of current shopping. And since this vacuum technology has increased, the knowledge of vacuum interrupting technology has increased so far, we have also decreased the current shopping phenomenon. And for vacuum interrupting, we do not need any surge arresters anymore because they do not generate any overvoltage anymore due to the low voltage current shopping.
Okay, so it was a good question, and we even have a better answer, kind of.
Yeah.
I would also like
please.
to add. I think I did mention that briefly in my presentation when we are talking about the short distances connecting GCB and generator. So we have a highly inductive circuit, short, small capacitances. So therefore, the TRV is nothing than the voltage occurring after the current interruption. So as Fabian mentioned, it comes from the history. So mainly used in the past is gas SSX circuit breaker. And there are two different switching media. So vacuum circuit breaker can handle very high TRV. They recombine very fast. So you want to know more about that, we can help with the explanation. And gas breaker are a little bit slower. So the requirement for GCB in the standards needs a higher RRV. There's some terms and numbers. So let's say if a media is not fast enough to recombine, it needs to add capacitance to cope with TRV. And vacuum itself is very fast, so it doesn't need. So that's just answering directly the question with the TRV of interruption. But I just want to add what Fabian has already mentioned.
Yeah, perfect. So thanks a lot for this comprehensive answer. That's why we have these experts here to give you as many answers as possible. And we continue the journey there. What does the Regi want to tell me? Do I have to? I need to come back in the. I mean, you experts are most important. So I'm just reading the questions. But yes, I am still here, not just the voice in the background. So FD asked, breaking current up to 110 kiloamps. Is this symmetrical current rating?
Yes.
Yes, that's a simple answer.
Yeah, correct. So basically, whenever we call our breaker or when we show a breaking performance capability, it's usually the one which is on the symmetrical current breaking from the system. So
yeah, that's what the standard requires. You have to name or rate your breaker with that value.
Yeah. And then KK wants to know, once again, we mentioned simulation a few times. Is there a simulation if we have a fault during out of phase synchronization at the generator end or at the system end of the generator circuit breaker?
I mean, out of phase mean you synchronize generator and the system, so the breaker is in between. So I'm not sure how to understand
because
the question.
What we are calling out of phase synchronization is mainly you ask the breaker to close
Yeah.
in not the right synchronization, in out of phase.
Yeah.
So what the protection relay will do right after, we say,
Nope.
open. And that's why we have to type test our breaker for out of phase. So
Okay,
we are closing a circuit which is faulty because of some issue, but the breaker has to open it directly, straightforward. And that's the out of phase synchronization we are saying. So the main duty of the breaker is clear the fault, even in the worst case condition, which is out of phase. So I would say by itself, the out of phase is one fault. So what we have to do is to clear the fault.
Yeah,
That's what we're doing.
they were asking for simulation.
Yeah.
So that's why.
Okay, maybe I didn't get the question properly. So
I
let's discuss
guess
further.
that we did some simulations
Of course,
before,
that's
so
like
that
part of my
we,
presentation.
yeah, so
We
that
did
we
that.
know that it
What is
works.
the requirements for the
Yeah,
breaker?
exactly.
Yeah.
So that would be my suggestion there. So then we heard something about inertia. Let's see now. It's moving here up and down. Let's see. The same is true for here. Let's go for the question from MAS. Why sometimes the fault doesn't interrupt by the distribution circuit breaker and sometimes by the generator circuit breaker too, and eventually cause a generator shutdown?
I can take over. I mean, first of all, it depends on what the breaker itself, whether it's distribution or GCB breaker is tested for. I mean, which duty can the breaker fulfill? Secondly, it depends on the protection scheme of the system. We get this as input to size the system. That's what I can say.
Yeah.
So it depends on what the customer has for a concept, and he says, okay, disconnect the breaker closest to the system, or always disconnect GCB first. That we cannot say. I mean, depending on the designer.
Depends on the philosophy on
Exactly.
site, right? Okay, thanks. And we take some more questions, I think. So RN wants to know, the M over C inertia is tied to cost. What's the driving element?
I don't know what MC means.
Me neither, but that's true. Inertia is kind of tied to cost.
Okay.
Any idea there what that means?
Okay, I guess maybe it's linked to my presentation because I highlighted the inertia as input
that's
information.
True.
I'm not saying that you guys need to modify your generator to fit our requirements. I'm just saying that depending on the machine and the inertia value itself, the results can differ. So do not modify your generator, just give us this information. That's what I meant.
Yeah. So the current configuration is important to know about.
Exactly.
You don't have to modify it.
Yes.
Okay, thank you. So there, next question coming from CP. So fast disconnecting faults means also high voltage peaks. Are there foreseen discharges of the peak values to protect the insulation of the generators or the motors?
Come back to TRV again, I think.
Yeah, I think firstly is this TRV value from the generator application when disconnecting that. I think I explained that firstly. And secondly is, of course, this current chopping level, what Fabian mentioned. So we are using a different type of contact material now in our modern vacuum tubes. So the chopping current level is much lower than before. So that's what he meant with the past and now modern contact material. And that's I mean, other parts we need to check, like what application has been dealing with, what kind of current is to be interrupted. But all of that can be simulated, and then of course there are standard and test duties for that to prove that.
Thanks a lot. And I think the next question we already heard an answer, right? What kind of simulation software is used? Do I remember it correctly? Something with no, sing and then
Actually, we are actually using PSS Netmark currently.
PSS, yeah, that's what I remembered. So almost correctly. Thanks for that. So let's see. KSA wants to know, what is the value of induced voltage after circuit breaker on load opening?
It has been explained before. I mean, the induced voltage always depends on what is the inductance and
Yeah.
resistance and so on in the circuit. The breakers are just open at certain time, and then when the current comes to zero, it can interrupt. So we need to know the info about the grid, about the system, to estimate, I would say, these kind of induced voltage. And then, as we said before, dropping current level is low, so it's all linked to the system value.
Yeah.
I cannot generally say how much this value will be.
Depends on the configuration
Exactly.
once again, right? Yeah. And then we go for the next question from CP. So in the older standards for grid circuit breakers, it was possible to close a circuit breaker having opposite voltages, so operator or scheme arrow, on the two sides without being dynamically and thermally damaged. Is it the same for the generator circuit breaker?
Yes, this out of phase testing duty.
Yeah.
It's defined in the -100 for distribution breaker, and is also defined in the GCB standard. So yes, it's the same for GCB.
No problem, right? Yeah. Oh, and then AA wants to know something about island mode. Can the Siemens generator circuit breaker operate with any generator protection relay for both island and non-island modes? And do you think that each mode should have individual protection settings based on different simulations?
Should I take over that one?
My specialist there. I think they came in during your presentation.
Okay, yeah. Okay, so the difference between island and non-island modes is just the numbers of, let's say, big transformers. So in island mode, you have a lot of smaller generators. So when we came back to our slides with this generator source current, we see a lot of delayed current zero. So in island mode, the possibility to deal with, let's say, relatively smaller current but higher DC component is quite high. So that's what you have to take into account. And in non-island mode, you have the stepper transformer, great higher current, but the DC components a little bit smaller. So that, like the short circuit current level need to be differentiated between these two modes, and the DC components where the delayed current zero or not need to be taken care of. And I know for a fact that the island modes or island networks usually have numerous number of generators, but of smaller size. So I think it's a part of at the end of the presentation of Fabian, the last few slides. If you receive the presentation later, you can see that.
Take a look on that.
Yeah, so that is what I can comment so far about the protection settings. About the timing, I don't know that, depending on your system philosophy, we can provide the protecting device, which can interrupt certain type of currents. Everything else, we need your input, how to simulate or, let's say, modify our simulation, just fit your need.
And what we'll do to select the right circuit breakers, we just take with the worst case scenario, just to be sure that in any case, whenever the fault, if the fault occurs, we are here to clear it. And then
yes, please. That's true. And we'll take one more question here from RN. Will the breaking time be longer for a generator circuit breaker due to no current zero crossing? I think that was in some of the diagrams, right?
Yes. So generally, yes, because you see the delayed current zero, and that's why there is a test duty, if I remember correctly, in the standard test duty 6B and something. If it says you have to test your GCB for dealing with delayed current zero, long time of minimum of X periods. So yes.
And that's the main difference between distribution breaker and generator circuit breakers.
Yeah.
And that's also why we have this specific standard, because of this requirement.
Yeah. And I'm not sure if we already answered that. What is the generator circuit breaker rating which is used for these tests?
I don't know what the type test. It's the rating of the device, and then we test each device according to the test duties. And let's say the HB1C is up to 72 Ka, and that's the value we test with all these remaining factor. HB3 is, for example, 110. So that's the value we start with the different testing Ds.
Okay,
So I
thank
hope
you.
I answer the question.
I think so. Let's see. I think we take one last question and the rest will be answered in a written form. You know that one. So we take that. I thought, I wanted to bring it in. So thanks for finding it again on the list. Knowing that it came in from JGM or JM, what?
Yes.
Yeah, exactly that. Thank you. So knowing that the genset cannot produce more than its nominal current, why breaking current is that much higher? Why? Well, can we monitor through SCADA? And now let's see what you make out of that.
Okay. I mean, each generator has a continuous rated current. I mean, the rated current can be rated short circuit current and nominal continuous current. But the continuous current is that what occur in a, what is a steady state in a normal operations. And then each device like generator, motor, and transformer has to perform short circuit tests. And from these tests, you get the short circuit impedances and reactances, what I mentioned in my presentations. And with these data, you can calculate this higher current. This is the short circuit current. I hope I understand the question right. And that's why the breaking current, when we're talking about breaking current, this is the short circuit breaking current. Of course, you can have this continuous breaking current. That's a different level. And because of that, I think the factor is usually 10 times different, like 10. The factor is 10 between continuous current and short circuit current. So that's why the breaking current, short circuit breaking current is much higher. It depends on the machine set itself.
So once again, depending on the configuration, right?
Exactly.
Yeah.
And mainly the way not we are monitoring, but power plant team is monitoring it, is we have instrument transformers within the enclosure, which is then helping our customers to have a view on what's happening on the voltage part, on the current part, and all of this information is then brought back to the DCS room or SCADA system, which is then using C-Protect relay, for example, a protection relay, will then define when it's time to open the breaker due to a fault. So, yeah.
A lot of information. So I think that probably your heads and your brains are pretty much filled with new and updated information. I thank you very much for being here in the studio, for delivering a lot of answers, for wonderful presentations. I hope that you remember that the benefits are that the HB1C definitely complies with the updated standards, that it flexibly fits to all of your or almost all construction requirements. Let's say, put it like this. I will not put my fingers into fire there for all, but I guess probably all solutions there. So I'm pretty much hoping to see you again in one of our next webinars around electrification and automation. If you have more questions to the experts, I think we put in the contact details. Hong just mentioned that there might be a wrong link into her LinkedIn account, but I think if you search for Hong Urbanek on LinkedIn, you will find her. You know how she looks like, and she will.
I think the link has been updated.
The link has already been updated, even better. And on the presentations, you get the contact data. So yes, you get access to the presentation, to the webinar recording, to any kinds of flyers we mentioned. There will be links in there. And I think in a few days, it will not be today and not tomorrow, probably, we will send out answers to the questions you had to the experts. So thank you so far. Stay curious, keep your assets protected, and see you next time. Goodbye.